Welcome to today's left brain lesson, which is all about numbers, one of my favorite topics. So of course we're going to start with some of the basics like integers and floats, depending on how much fine-grained control you need. But then we're going to talk about rounding numbers up, depending on how many digits out you want things or how you're going to print them. We're going to talk about the difference between casting and coercion, so it's whether we want to change things specifically from one type to another, or it's happening automatically in the background. I'm going to show you some of the constants you can bring in, like pi or e, and then some Boolean math, the thing a lot of people don't think about, but 1 and a 0, the true and the false, these are definitely ways that we can calculate. And then, of course, working with some random sequences, how do we get random numbers generated? And then how do we print those to a console in the way that makes sense for whatever the application or program is that we're doing? So stay tuned, stick with me, and I can make sure that you never go bald. Let's talk integers, shall we? So here's some basic integers just to review. We can have a -17, a 0, or 42 as long as we don't have decimal places. Also note this notation. So see, I have int1, int2, int3, and I'm just using commas and then assigning them to these three. But this is just like before when we made variables, a little bit different syntax, a little more compressed. But we can print them all out in the same way by just putting commas between them, and you can see that they work just fine. And we can check them to make sure they are of type integer. Okay, now let's talk float, get some of the basics. So we're going to make a couple variables here. One we're going to set to the integer 21, one to the float 3.1415. And by printing out the types, you can see that we get exactly what we were hoping for. We get an integer and a float type. But here's a good question. So how many decimal places do you think that we are going to get when we run this cell? Because we input 4 after the decimal, and we get 4 out. Okay, so Python doesn't have any problem with that level of precision. But what about this? We're going to import a constant, pi, which goes on, as you all know, forever. So how many decimal places do you think it's going to print out for pi? Okay, so this is going to be its normal limit. So that's the precision level that we're dealing with. Usually not a big deal, but just something to kind of keep in mind that there is different levels. And at certain times, that's way more than we want to show someone. So if you want to tell someone what pi is, 3.14 is usually good enough. So let's move on to the next topic and talk a little bit about rounding. Let's look at how we would do that. So let's make a variable, and this one has many digits after the decimal, and we can use this cool function round. And it puts in the variable and a parameter which specifies how many digits we want to round to. And then we're also going to wrap that again in this second function called type, just to make sure we are still dealing with a float. So when we run this cell, we get that it's still a float and that it's now down to just 2 digits, okay? Now, if you don't put any parameters into it at all, it's going to actually assume 0, and it's going to move it all the way up to an integer. And it's a different type also now. So the important thing to remember is that if you round all the way up, Python's going to try to save memory, and it's going to turn it into an integer, and it's not a float anymore. Also, let's talk about if you want to round in certain ways, because sometimes what they call ceiling or floor rounding makes more sense, meaning no matter where the digit is, just bring it up or bring it down. And there's a couple things we can do for that. We can import a module called math, and then we can wrap it in a function called math.ceil for ceiling or math.floor for floor. And you can see it's going to round it up to 9. As you can see, it's going to round it up to 983 or down to 982. Let's talk casting. So let's make a couple toy variables here. So we have a negative float and a regular integer. And now I want to use an absolute function. Okay, so you remember from mathematics, absolute numbers are non-negative numbers. They're a distance away from something. So we can actually run a float, -3.14, into an absolute function and get out an absolute number, which is a cool thing that Python can do. And remember, we didn't actually make my float back into this absolute number. We just referenced it, made an absolute value, and viewed it. So when we cast our float into an integer, what do you think we're going to get? Did you guess -3? Because we still have the negative up there. We didn't actually overwrite it. We just displayed this. So another thing to remember is that the state of the variable, it can be very different from what you're outputting on screen. So let's look at another casting. If you're going to take my integer and turn it into a float, my integer right now being 21, what do you think we're going to get? 21.0, right? Like it's just the same number. The other one you can kind of think of as having a 0.0, but it's going to take up more memory now because it's remembering more precision. Also want to talk about complex numbers. Not that they really come up that much in regular life, but they are cool. And I'm sure you remember in mathematics how fun it was to, use angles to solve, multiplication problems. And, that stuff's just kind of cool. So knowing that Python has complex ability is neat. We can actually input 2 digits here. It's going to be where on the x-axis something is and where on the y-axis something is. The 2 integers here, or 1 float and 1 integer, are going to give us 21 to the right and then negative 3.1415 down. You can think of j as the y-axis. So it's cool to know that it has that. And we also have hexadecimal. So in reality, the only time hexadecimal comes up in my life is like with colors. Sometimes working with Photoshop, things like that. But there is a conversion because that's a base 16 system. But we can convert the number 78 to hexadecimal and get 0x, 4e or whatever it is. And we can do this with any number we want. So we have a conversion and we can convert back and we can do all sorts of cool things through casting in Python. Coercion, very similar to casting, but it takes place behind the scenes without our knowledge. So a good way to think about casting is that it's explicit, it's a decision that we make, and then coercion is very similar, but it's happening implicitly. It's happening behind the scenes. Python's just making it happen so it can solve problems for you. So easy example, we have 1.0, a float, and we're going to add it to the integer 2, but after running through the function float, which turns it into a float, and you'll see that we end up with 3.0, okay? Now, if we actually add 1 directly to the number 2, we get the same answer. So behind the scenes, it's just saying, whoa, 1.0 can't be added to just 2. I better turn 2 into 2.0 and then do the math. Next, let's talk constants. So a few constants that commonly come up are pi and Euler's number. So just so you know, how you get those is by importing the math module. So once that's imported, you can run math.pi and you can get 3.14 yada yada, and you can run math.e to get 2.718 yada yada yada. So that's great. Sometimes we don't have to type all these things out. We just throw in math.pi or math.e, or maybe you even assign that to e and you do something like that, and then throughout your code you can just use e whenever you need to. So there you go. Food for thought. Let's talk Boolean math. So this is just kind of an interesting thing to have in your head, that false and true also act like the numbers 0 and 1 in Python, and they can actually be used as replacements for 0 and 1. So we're going to assign a couple variables here, just f equals false and t equals true. And you can see that we can simply just do 1 plus f, right? So f is going to be 0, so 1 plus 0 should give us 1. 1 plus true, so it should be 1 plus 1, which is going to give us 2. And then we can do 1 minus false equal 1, 1 minus true equals 0. So cool little thing we can do there with Booleans. So now let's talk about randomness. So randomness actually seems to come up a lot when I'm programming, and I wouldn't have thought it when I started, but just the way the world's going, especially with like neural networks and some of the kind of cutting edge stuff that we're going to eventually get to, it's all about controlling uncertainty. It's about having a grasp on randomness. So, in the super basic sense, what we can do for a random number is bring in a module called random. And I'm also going to make just a little sequence here that we're going to use in a couple cells. But if you want a random number, it's as simple as random.random open close parentheses, right? It's a method inside of the random module. So we run that and we get, in this case, 0.04 or 0.04, but it's always going to be a number by default between 0 and 1. And there are a whole bunch of parameters, so make sure to wrap that thing in help and go Google it if you're interested in all the other ways you can generate random ranges. But you can see by just running this over and over again, we're going to get a different number between 0 and 1. And one of the cool things that you can do with sequences is you can use random.choice. I find this really powerful if you want to pull something out of this sequence, like you want a random thing out of a database, or you want a random item pulled out of some kind of a list or a dictionary. You can use this random.choice, and you'll see that it's going to pull out the number 6 in this case. But if we just keep running it, we get 2, we get 6 again, we get 6 again, we get 6 again, we get 4. So it's a very cool way you can pull that out of lists using the random module. Okay, and finally, let's talk about just how you would print these things, because it's not really intuitive to always see tons of numbers after the decimal. So let's just show how you might want to print this out in a way that's more human intuitive. So we make this float, which has a whole bunch of numbers after the decimal, but we can say in a format, in a print format, my float, and we can actually just reference it and see everything, or we can use a :.2f. And remember, this is different than needing to round it first and then printing the rounded number. The whole number's still there in memory. We still have all of the precision that we had before, but in a simple way, we can actually just print out that it's National Pi Day. Subscribe to the Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations. Welcome to today's lesson on strings. Very excited to talk about strings because there's so much we can do with them. And we're going to start by going over the basics, how to print them to the console, how to format them so they look nice when we're printing for the user. We're going to talk about slicing them up on an individual character level, going from one character to another and then taking pieces in between. We're going to talk about concatenation, which is the process of putting strings together again, merging them. We're going to talk about escaping, which are special characters that we can use to get out of strings and put in information that gives it much more power. We're going to talk about raw, which is another type. It's an input type that lets the user type things to us. And then we can change those using casting into numbers or floats or whatever we need to do with them. We're going to talk about Reaper, which is a function that doesn't print in the same way a human would read it, but it does in the same way that a computer thinks about what it's giving us. And it can be really useful in a lot of situations. Then we're going to talk about encoding. So we talked about everything being UTF-8 inside of Python. So we're going to look at all the different fun characters we have, how we can use them. And then we're going to use an ORD analysis to actually figure out what's going on behind each of the characters. And then finally, we're just going to show off a bunch of methods. I don't have enough time to go through everything, but we're going to look at how to change the cases and strip them in different ways and do alignments and finds and replaces and splits and oh my. Let's hop into the deep end of strings. So, the basics. Okay, Python has a built-in class of strings. You'll know this as str when you search for the different types. And here's an example. A best friend is like a four-leaf clover, hard to find, lucky to have. I'm going to put that string of text into a variable called friend. And now I'm going to make a couple more of those and look at the different types. Okay, they're both strings. Makes sense, whether they have spaces or not. Now, here's a question for you. The number equals 5, but it's in quotes. Is it going to be a string or an integer? Well, we should know this. It's going to be a string, an str. And that is because of the quotes. Okay, now let's talk about the basics of printing. So, of course, we have double quotes, which we're starting to get used to for making a string variable, but also, don't forget, we have single quotes. And the reason you might want to use a single quote or a double quote in different situations has to do with the text inside. So, in this example, it's National Pi Day. We have a contraction that uses a comma. So, we're going to want to use maybe double quotes, but also maybe we have double quotes inside, so we want to use single quotes or some kind of mixture of them. So later we'll look at some other ways to handle that, but just in a basic understanding, either of these, they're just identical. They're the same thing. So let's look at some formatting issues. Now, formatting becomes a big thing. You're constantly printing, you're constantly writing things out, and knowing how to make it all look right and spaced right and read right for the user is a big thing. So formatting is one of those kind of core concepts in programming. So let's make a couple variables here. We have one that's called pop and another one called tart. Of course, brother and sister, I assume. And there's an old style of printing. This does work in Python 3. It also works in Python 2. You'll see it a lot, but it's not the recommended way. So I just wanted you to see it, but not really use it. And that is to print out this %s, and then use a percent in the middle, and it corresponds to the two variables. So when you run that, it does work, but it's not the preferred way, and there's a lot more powerful things you can do when you use this .format function, okay? So this is the way we should be printing things. Print, you open the quotes and you close them, and somewhere in between where you want the variables to show up, you use these double brackets. Double bracket, okay? So we know that var1 corresponds to pop and var2 is tart, so it should say dang, comma, my pop was tarted. I know. Okay, so there we go. Boom, worked just fine. But here's some cool things we can do now also. We can also put the order of the variables in any order that we want in the brackets. So This one will go first, then second by default. But look, now we can say make this the 0th, because Python often uses 0 for the number 1 slot. And then number 1, meaning number 2, for this one. So when we run this, you'll see we get a reversed order. Dang, my tart was popped, you know? It's very cool. And in this one, we're doing the same thing, but now we're adding a duplicate, okay? So now we have 0 twice, which, no problem. We can do that too. So you can see how powerful it is to use this dot format with an open close parentheses, because they're variables that are being passed in as parameters. Okay, now let's look at some slicing. And, it might not be an intuitive word, but what we mean is we're taking the sentence up. Imagine it like a carrot, and we're slicing it into little pieces. And each one of those pieces is the different characters, the K, the N, the O, the W. So we're going to make a new variable here called knowledge. And now let's talk about some of the functions we have. Like we have len, which comes up a lot, and it's actually going to count how many characters there are inside. So count them for me, and then take a guess at what this cell is going to return. 55? Whoa, that's a lot, but it's also correct. Now, here's a question. Does it use the space as a character or not? Holy crap, I don't know the answer to this. I just asked it and thought it up right now. 1, 2, 3, 4. Yeah, 55, that includes the spaces, because spaces are going to be a Unicode character too. And now we both know. But let's look at slicing. So we're going to take knowledge and we're going to put this different type of bracket. Notice the square bracket that we're using, not the normal parameter parentheses, okay? This is a different thing. This is slicing. And when we say 7, what we're saying is go in 7 letters. 0, 1, 2, 3, 4, 5, 6, 7. We are going to be returning a G, okay? Now we can also do a slice that's a bigger chunk. So instead of like little thin carrot slices, this is just like cutting the carrot into thirds or something with larger width in between. So in this case, we're going from character number 7 to character number 20. So what do you think is going to happen when we run this cell? Okay, we get GE is only A, and this is the slice from 7 to 20 through here. Now, what about if we use 0 and then comma and then -1? Whoa, what's a negative? Well, Dylan, we haven't even talked about a negative. Where does that go? Well, I kind of gave it away with my mouse, but take a guess, and you can see it's an E. So it looped around, okay? We have E because it's at the very end. And this is another really cool, powerful thing. Sometimes you have these long lists and long sentences and things like that, and you're going to want to start from the other end. Start from the bottom and work your way up instead of working your way down. Now, we also have in between first and last letters, so we can do 1 colon -1. And that's a little confusing because one's a looped around and one's on the front end. So what do you think we're going to get? Oh, everything in between minus those two on the side. So, it kind of, went around and just took out the ends, right? It chopped the ends off the two sides. And then I want to also show you that we can use some of our membership conditionals that you're going to learn in the next section, but it's really cool to just ask, is the letter E inside of the word knowledge? Because behind the scenes, they're kind of working like lists. So we can do that too. True, E is in knowledge. You can see it right there next to the L and behind the D. Okay, now let's talk about concatenation. So one of the things that we want to do at certain points is take these slices and put them back together, right? Like two strings can be merged together. So here's a couple of variables I've created. Popsicle, knuckleball, and then a sequence, which is all made of strings, 3 strings, Alvin, Simon, and Theodore with little dashes around them. So let's go ahead and make those variables, and then let's do this. It's a concatenation. Pop string plus knuckle string is equal to this new variable x. What do you think is going to happen when we print x? It squished them all together, right? Popsicle, knuckleball, right? Now, what if we do multiplication? What do you think we're going to get when we take something that's a string and we multiply it by 5? 5 times, easy, cool, huh? It's just popsicle, 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 everywhere, popsicle, popsicle. Now, what if we concatenate a sequence, okay? So we have our Alvin, Simon, Theodore sequence above. What if we use pop string, which has already got some kind of a variable in it, our text, and then we do dot join, we bring that method in, and we pass in an entire sequence. So this is kind of confusing, right? Like we actually have pop string, which is its own variable, and we're passing in this sequence. So what do you think we're going to get? Alvin, popsicle, Simon, popsicle, Theodore. Whoa, blow my mind. But there's some very cool things like join that we can use to put these together, and that's a process called concatenation. Now let's move on to our next topic, which is escaping. basically saying that there are certain patterns that if you put them inside of a string can break out of the string. But most importantly, it's this one character that's used most often. It's a backslash, okay? So remember forward slash and backslash, this is the one that has the top leaning to the left. It's the Leaning Tower of Pisa falling to the left. And when you use this, in between what should be just a normal string, it's going to break out the next character. And the next character in this case happens to be n. And n is going to create a new line when it's broken out. So in this sense, take a guess what you're going to see. Is that what you expected? It takes hi, it adds the space. There's actually a space right here. That's a character that came in. And then it sees this and says, okay, the next character is going to make me do something different, not something that normally would be inside of a string. Oh, it's the letter N, create a new line, and then ho. So we have hi-ho, hi-ho. It's off to the next cell we go. And in this one, we're using the letter T. Now, T is short for a tab. And some of these things you're just going to have to memorize, but as long as you understand the concept of escaping and you're trying to do something with text, you can probably go look up some of the other characters that you can escape, and depending on your use case. But as long as you know they're there, you can do really cool things, like combine it with multiplication. So just like before, what do you think we're going to get when we multiply an escape character and then n with 5? Yeah, 5 new lines. Check down here. Line, 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 line. Now let's talk about raw input, which is something that is super cool. It's the ability to simply ask the user for information, text, numbers, integers, and then use it in the same way as we've been using everything else. So here's an example. If you wrap this string, what's your name, in a function that starts with input, what do you think is going to happen? Well, let's find out. What's your name? And then this cool text box. Look, I can name myself whatever I want. Bozo. Okay, well, what happened now? Well, we have a variable here that we set this to, so let's check what's in it. Bozo. Cool, huh? So it just prompts the user to input things, and then if you're working with websites and things like that, you can actually style it so it happens in different ways. But at the core of it, this is Python's way for you to just type input. And one of the things we can do is actually cast before dropping it into our variable. So you can see how that could be sort of convenient. If we were to take an input and it was some kind of a number, we might want to cast it into a float because we'd want to do a calculation with it. I mean, I do my fingernails probably 3 times a month, but yeah, once a month. Okay, so the number 1 goes in, and because of the .0, we already know that it's a float. Couldn't have done that in any other way, but I suppose just to show you how the proper way to do it is, because you don't always have that hint, would be to wrap it up like that, and you'd see that it's a float. Okay, cool. So what if we want to take, how many times each month do you cut your fingernails, and turn that one into a float, and then we want to use some concatenation. Maybe we want to add them. Actually, so this is actually that's an interesting mistake I just made. We could probably learn from that. Plus will concatenate it if these two are both strings. But we have changed them both into floats. So the plus is just going to do what plus does always in math and add the two together. Okay, so next question is, how many times each month do you cut your fingernails? Well, I cut them 3 times on average, precisely. So we run that. Now we can actually add the two together and put them in a new variable. And we can have the total of 4 times a month on average. I'm cutting either some kind of my nails, I guess is the way to interpret that. Now let's talk about this Reaper function, because I find that it's a great way to see how we interact with computers versus how a computer acts with the computers. Okay, it's like catching it in its own little environment. How do you talk to yourself when I'm not around, you know? But if we import this module datetime, which you don't need to know, we can make a couple of these variables based on date and time. So let's just print these out using a normal print. So what we're saying is take the information that came, turn it into a string, cast it, and then print it out. So you can see the format, the 2016 1204, and then the hour, minute, second, and like super decimal second. Okay, now I want to take the same variables, but now instead of printing them out with string, let's print them out with the Reaper function and see the difference. Now in this case, it looks quite a bit different. It says datetime.date, which is similar to how it's up here, datetime.date, and then .today. This function, this method right here, is now replaced. And just to remind you guys, it is a function, but it's also a method because we're accessing it through the dot syntax. But you can see it's a little bit different. This is more of how the computer sees it and views it and thinks about where the information came from. And this is more about how humans would want to read it. So sometimes it can be great to run different things that you're trying to learn about through the Reaper function just to see kind of a more structured way of where they're coming from. Now let's talk about encodings. I want to build on that UTF-8 statement we made in the new mnemonics. So ASCII is a different set of characters. This is the one that you could have found in some places in Python 2 or Python 1 and what you find in older computers that's now been totally removed from Python 3. But it's the characters that kind of I'm most familiar with. They come on the American keyboard. But look at this. If we actually make a variable and we put a string in it with ASCII characters, in Python 2 we could have asked, is this instance Unicode? Like we could have said, is it ASCII or is it Unicode? We could have checked for it, but we're going to get a warning now because everything is Unicode. And that threw me off because it's saying like Unicode's not defined, but it's just because it's baked so deeply into Python 3 that we don't need to check it all the time. And that means we can just write variables like this, strings that have whatever that is, the umbla, I think, or umla or something, and then, cool Japanese characters like that, they can just be written right in. And one of the cool things about this is that with Python 3, we can actually just use Unicode. We can use Greek letters that come with Unicode, so we can use the pi symbol if we want to just set math.pi to, the pi. We can use the Greek letter epsilon, the capital one, if we want to use something for like sum, and it makes it very cool. We can use all these like copyright icons and things like that inside of our code to, explain things better to other people who are reading it and to remind ourselves and, just be badass programmers, really. Okay, and then I want to talk to you about this function. It's called ORD, and what it's doing is it's linking a specific Unicode number that we don't see but is actually behind every character. So in an ASCII character like A, there's going to be a specific number in Unicode UTF-8 that is going to correspond to the capital letter A. So we'll have another one for the capital B, and you can see that they're separate, but then when you actually go to lowercase, they have their own numbers too. So this is how it's keeping track behind the scenes of all these characters. In fact, I think I could probably even take like this Greek epsilon and throw it in there, and then it's going to have its own number, and it's always going to be that same number. So that's going to correspond with what we see on our end. Okay, so just one other use case for this I want to show you is that we can use a for loop, and I know you haven't seen this before, we'll talk about it later, but just kind of observe it and get familiar with it on a sort of superficial level to actually run through every single character in a string and show us what the character is that corresponds to the UTF-8. So, that capital I is always going to be the number 73 behind the scenes. Okay, now let's talk about some methods that we can use with strings, because this is really where the fun stuff is. Okay, so finally let's talk methods, and there's way too many to cover everything, but I just want to get you excited about some of the big groupings and the stuff that I use a lot. So let's start with a new variable that's a long string, our best friend string, and now we can actually use the method .capitalize to make sure it starts with a capital. In this case it already does, so you don't say anything, but that A at the beginning right there is because we ran it through this method. And we can go further and use some other cool ones like upper. We can make everything lowercase. We can make everything title case so that each letter has a capital at the beginning of it. And we even can do checks. So you can take a string variable and you can say .is upper, and we're asking give me a true or false response if it is all upper or if it's not. And you can do that to then trigger the change. So you can say, hey, bring me a bunch of text. If it's not already in title case, then make it in title case or something along those lines. There's also some really cool ones that we can use with strip, and this is going to remove white spaces. So if we have an input function like a raw function that we looked at before and somebody types in some stuff with a bunch of spaces at the beginning or end, this is going to strip those clean. We also can remove the leading white spaces or just the trailing white spaces. Kind of hard to see these, but they would be spaces that would be over here, over here. We can also do some cool stuff with alignment. For example, this one .center is going to bring us a method that allows us to put 50 characters before and after. It'll take that number and split it between the two and put them on both sides to help center your text. And there's some other cool alignment ones too we don't have time for, but I want to get to find. So if we take this string here and we use .find clover, it's actually going to parse through the entire thing and find the word clover, and then it's going to count how many spaces it went before finding it, so we know that it's 34 in. There's also this one that counts characters. We're looking for how many times the letter A in lowercase shows up, so like 1, 2, 3, 4, like that, it will count it and return that there's 4 in the entire string. And the max and min, which you might think of usually only in the terms of numbers, are also in alphabetical order. So it can say, you know, is there a Q, is there a Z, what's the maximum height letter inside of this string? And we can see that it's a Y, and we can do the same with min. I'm sure it'll find an A. Oh, actually a nothing, yep, so even before A is a space. So it's really cool. There's a lot of neat things you can do with find and replace. You can actually go in and say, take the word clover, right? Which this can be a really useful function. And we know where that is, right here. And then we say, replace it with snickerdoodle. Then boom. A best friend is like a 4-leaf snickerdoodle. That is very cool, and it can do some of the same things that you can do with slice, but way simpler, more automated, especially with big corpuses of text. So let's make our friend variable, and then let's just run .split method and see what happens. Whoa, how cool is that? It broke out our entire sentence into individual words. And it does this by any delimiter we want. So we didn't put in an argument. We passed in nothing. So it just did a default, which is to look for these spaces. But check this out. We can also add in the string with a comma in between it, and it's going to look for these and split at the commas. So see, now we have a list that has 3 different items in it, and it's the ones between the commas. And we can do that with all sorts of stuff. You can make maybe LE is where you want on yours to be, or I don't know, some kind of crazy array that makes sense to you. And the last one I want to talk about is split lines. This is just like split, but what it's going to do is automatically do it on the character return. So if you had a large corpus of text that had paragraphs, this would break it in each paragraph into their own item on a list. Very cool stuff, lots of neat methods. I encourage you to explore. Oh, and remember, what about this? In fact, before we end, I will give you a reminder of something else we learned. .tab is going to let you look through all of these cool things. So I encourage you now to just go through and play with them all, see what else you can do with the text. Subscribe to the Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations. We will be learning the how of programming by reviewing code examples that demonstrate how lists work, including some of the various subtopics like how to view a list, how to insert new items into a list, how to find certain items inside of a list, how to retrieve the specific item that we find, how to remove items, combine, sort, all of the stuff that we might want to do with lists. Then we're going to talk about range, and range is a really powerful way to make a list. It's a way that we can specify huge lists without having to go in there and manually type everything. And then finally we're going to talk about matrices, which are really just lists inside of lists and different things that we can do to break them up and flatten them down and look at them in different dimensions. So let's get ready to talk about the all-important Python list. Definitely one of the most powerful types in Python, comes up all the time as a programmer, and you can see why they're so powerful. They can hold integers, floats, strings, they can hold lists of lists, and they all have a few characteristics. So we start with a variable, we use an assignment operator, this equal sign, and then we open a bracket and close a bracket, the square brackets, and inside we put all sorts of different elements, which can be different types. They can be strings, integers, floats, etc. They can be all sorts of different things. And elements are just broken up by these commas. So you can see how easy it is to make a list. And then we can even put lists inside of lists, and they will be broken up in the exact same way with the comma in between. Let's run this cell. We now have 3 lists, our scores, tax code, and mixed. And now let's look at how we view it. So if you're using Jupyter, of course, we have individually running cells, so we can just write scores, which is going to return it. And of course, if you're using an IDE or some kind of other interactive way to work with Python, you could use the print statement and it would do the same thing. And here is something I haven't talked about yet, but later we have an entire video devoted to for loops. So don't worry about the syntax too much, but one way to think about this is that this is a special way to address some kind of logic on each individual element before passing on to the next one. So it would be like, multiply 3 times 3, and then multiply 1 times 3, and then multiply 4 times 3, or whatever it is. In this case, we're just printing that we can break them into their own lines. And now inserting is going to be one of the most common use cases. You're going to maybe create a list, and you're going to want to, scrape the internet and like tack on a whole bunch of things to a list, or, whatever reason, a database of some kind, and you're going to want to add things to. And any variable that is of the type list has a method called insert. An insert requires 2 arguments. The first one is the position that you want to insert the element in, and the second one is the element itself. I've got a question for you. Here is our tax code list. You can see that it's Bamfuzzle, Cattywampus, Gargaloo, and Billingsgate. We want to add a loophole to this tax code, and we have specified the number 2. What position is it going to end up in? Take a guess? Is that what you thought? The 3rd position? So this is a reminder that Python uses 0 indexing. So this is the 0 number, this is the 1, and this is the 2, which makes sense when you think about it from a computer's point of view, but it's not necessarily intuitive to how we would normally count. Normally you would say this is probably the 3rd item in a list, but it's not how Python works. So it's just something to remember. Now, another really powerful way to add an item to a list is to use the append method. And this is really powerful because we don't need to know how long the list is. Instead, we can just say append, and no matter how long the list is, it's going to put this on the end. When we run this cell, you can see that we now have added our loophole, our was loophole. So now we added our was loophole to the end. So now Bamfuzzle, Cattywampus, Loophole, Gargaloo, Billingsgate, and was loophole are all inside of the tax code. So how are we going to find one of these list items? Because these lists, you could imagine, become thousands or maybe even millions of elements long. How can we find something in an efficient way? Well, Python gives us some really powerful methods to do that also. So here we are making a new variable called letters, and we're creating a list that holds the string. These are single character strings. P, Q, R, S, O, and U. What we can do is actually say, here's the variable of type string, dot for accessing our method, use the method index, and check to see if the list is holding the string of character R. So when I run this cell, what do you think is going to happen? Because you'll notice that there is an R, there is a P, but there is not a Z. Okay, well that's what we expected. So it's actually a little more powerful. Okay, so that's what we expected, right? We have R, which is in the 2nd position, 0, 1, 2. We have P, which is in the 0th position, the very first one. And then we have Z, which is not in the list at all, so it throws a value error, not in the list. You can imagine how powerful that would be if you want to look through, a database of names and say, is this name in there? Another thing that we might want to find out is how long is our list. So we can simply wrap that in len for length. When we put our variable of type list in there, it will return 6 for the 6 items. 0, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6. So here you can see that it actually does return how many individual elements there are, and we don't need to think about it in the terms of 0 to 6. We just think of it as 6. A little tricky there, but just something to keep in mind how Python indexes sort of on 0, but there's still only 6 elements in it, But I feel like that's one of those things that just trips up everybody. Even good programmers are just like, why didn't that come? Yeah, oh yeah, that's right, 0 indexing, So retrieving something out of a list is also very important. Okay, here's a reminder of our tax code. Bamfuzzle, Cattywampus, Loophole, Gargaloo, Billingsgate, was loophole. So if we want to retrieve an item, there is a very special syntax, and they call this slicing. Whenever you see these 2 brackets surrounding integers, we're slicing a list up. A couple things to note here is that this is very different from space equals that. That's creating a list with the integer 0 in it. This is assuming the list already exists, and it's this variable tax code, and we want the 0th element. We want Bamfuzzle to be returned. Let me run this cell and show you what I mean. So you can see it's actually saying Bamfuzzle, and what if we put in 1? It's going to bring in Cattywampus, or 2. So this is a way to pull out the 3rd element or the 2nd element from our list. And we can also slice out groups. Very commonly, you're going to want a range of things. So here we want 1 through 3. Now remember, our 0 indexing makes this a little confusing. Why don't you take a guess? We have 0, 1, 2, and 3, and we're specifying give me everything between 1 and 3. So, if you haven't seen this before, you might think, well, it could bring all of these 3, it might bring just these 2 or just these 2, but let's run it and see. So we get just Cattywampus and Loophole. So by slicing the index 1 through 3, we're ignoring 0, makes sense. We're starting with 1, then we're getting 2, and then surprisingly we're not getting 3. So that's just a reminder that the third element is kind of the one that you ignore. It's going to capture the one right before it. It's not going to include this, but it is going to include that. So I always think of it like this one's included, this one's not included. Now another interesting thing about slicing is we have the ability to use negatives. So what do you think a -3 is going to do? Take a guess and then we'll talk about it. Gargaloo. Okay, so it brought us this one. Let's look at why. -3 goes backwards. It loops around the list. We can always assume that this first element is 0, and then we can count up. 1, 2, 3, or in the case of a negative slice, we actually jump and loop all the way around to Woz loophole. So -1, -2, and -3. Okay? So the way to think about that is, actually let's see, 0, 1, 2, 3. Let's not use 3 because that is actually the same either way. But something like Billingsgate, you can think 0, loop around, -1, -2. So negatives are another really powerful way to jump to the end of a list. Now let's look at how we can save a slice. Just a reminder, here's what our text code looks like. Slicing is very powerful in its shorthand notation, where we use those brackets with the colon or an individual number, but it's also its own function, and its own function comes with more parameters. In fact, it has the ability to step, which is an interesting property. So what we can say is I want to get every other element, every odd element, or every third element. So here there's a function called slice. Now, if we look at some of the parameters using our nifty shift tab in Jupyter, we can see that the first argument is for where the slicing starts. The second one is for where it stops. This is very similar to the colon. But then we also have this thing called step, meaning take every second item. So I will save this into a variable, and then we will pass that variable into here. Now remember, that's the same as taking this and doing that. You have something specific you want and then use it as a variable later. But it can be used either way depending on your purpose. So let's go ahead and make that slice. Now we can see slice 0, none 2, just what we specified. Now we're going to pass that into our text code and we get out every other element just like we asked for. So it starts with the 0th element and then it doesn't take 1, but then it does take 2, and then it doesn't take 3, and it does take 4. Very cool pattern. Now if we do 1, that's going to be the same as just arrange. That's going to give us everything. Or if we do 3, it's going to jump all the way to the third one and just give us Bamfuzzle and Gargaloo. And if we had another element there, it would bring that back too. So very cool way to retrieve items. Now how about removing an item from a list? Because this is another very common thing. Well, it's as easy as using the remove method. Taxcode.remove Bamfuzzle. Of course, we won't get rid of that loophole. But now Bamfuzzle is gone, so you can see right here, that was the first element in our list. It went Bamfuzzle, Cattywampus, Gargaloo, and Billingsgate, and now it's just Cattywampus, Gargaloo, and Billingsgate, just what we wanted. Now let's look at some fun ways to combine lists together. So there's a lot of powerful things we can do here. I won't cover them all, but for example, what if we have a list here of strings? It's all different strings, no integers in here. Code, Mentor, Python, and Developer. Now, if we take this variable and we pass it into an empty variable of type string, and we use the join method, it can actually combine these together. So if I went, I don't know, feels like I went kind of fast there, but basically we have our list, okay? It's all made of strings. And then we're saying, just forget that for a second, and now we're saying over here, make a new variable, and it's got a string inside of it. This could be words, but it's not. It's just empty. It's just one space character. So the string is of one character, and it's the space character, so you don't really see anything, but just know it's a string of one space. And then we're saying, hey, you're of type string, and you have a special method called join. So when you pass in a list, the join is going to combine all of these together. They're not separated anymore. This is all one word. This is like a paragraph or a title, whereas these are individual elements inside of a list. Now lists can also hold different lists. So an example of that would be here. We have a list called things, and it's holding strings, it's holding a string, an integer, and then a whole nother list. And this list has 2 more integers, and it also has another integer that's coming in through this variable numbers here, and that has a float. Now here's a syntax that you don't need to know yet. We're going to cover this in later videos, but one powerful powerful thing I just wanted to show you that we can do with lists is we can break a string apart into individual characters and then put those individual characters back into a list. So don't worry too much about this. It's called the list comprehension that we're going to talk about later. One of the cool things it can do is take a string, 1 space 2 space 3, and break it into actual integers. So we've cast it into an integer here, and these are 4 different integer numbers that we could do math on, and they started out as just numbers that were inside of a string. So maybe you can imagine some situation where you're, parsing some text and you're pulling out numbers and then doing math on those numbers. Kind of cool. As long as we're talking about these lists inside of lists, we're basically making groups, right? So let's look at a couple different ways that we can do some more powerful grouping. We have a list here that's just full of a bunch of integers, a bunch of random numbers, and one of the things we can do is create groups of either 3 or 2 or 4 or whatever we want. Now don't worry too much about the syntax, this is kind of later in the course kind of stuff, but I want to show you that we can actually make an awesome group of 4, or we can make a group of 2. So we've taken all of these elements up here and said make those to a group, make those to a group, make those to a group. And this group is technically called a tuple, but we'll learn about that in the next video. So it's really cool to be able to take lists and break them up like that. And another neat thing that we can do is actually count them. So this really cool method called max, we can pass in a list, and then we can look at a key called x.count. So we can find out that the number 1 is the most common. You can see that number 1 occurs 3 times, and all of the other ones only occur once. So pretty neat stuff we can do. That's just the tip of the iceberg when it comes to combining. Let's talk about sorting. We'll start with a couple lists here. These numbers are not in order, and these words are not in alphabetical order. So just note that to start with. And then we can actually just run them through a function called sorted, which is going to look for either the smallest to largest number or the alphabetical setting. If we run scores through this function, we see that we're now in order, 1, 2, 3.3, 3.3, etc. And another syntax for that is using a dot sort method and then passing nothing into the parameters. So starting with tax code, our list, we can actually use that syntax to put these in alphabetical order. Billingsgate, Bumfuzzle, Cattywampus, and Gargaloo. And then finally, I just want to talk about one way we could reverse a list. We could sort it in backwards order, and that would be to use this -1, saying sort of go backwards with a couple colons before it. And by using this, we can actually sort backwards, so Gargaloo, Cattywampus, Bamfuzzle, and Billingsgate will be in the reverse order. Now we have an idea of sorting. So we covered a lot. This is an area where you're going to want to keep playing with lists until you get more familiar with them. But now let's talk about ranges, which are a really powerful way to make lists. Next up, let's talk about a special function called range, and it has a lot to do with the way lists work. There is a function here, and it's called range, and it takes a minimum of 1 parameter. So if you give it 1 argument, it is going to create something of type range, which is different than type list. But in this case, we're going to want to be using them in the sense of a list. So instead of leaving it at range 6, we're actually going to always be wrapping it in this list here. We can get range to return a list of 6 elements, 0, 1, 2, 3, 4, and 5, 6 elements here. And imagine if we wanted this to be 1,000,000 long or 100,000 long. Now the way to think of range with 1 argument is that this is the stop argument. It's going to start at 0 and it's going to go until it's got 6 elements and then it's going to stop. But we can also specify in between some kind of a range. So we can have a start element and a stop element. And in this case, going from 3 to 6, just like with list slicing, this is like list creation, but it's going to go from 3, 4, and 5, creating 3 elements. And just like the list slicing, it's going to take the start argument and actually make that the number, and then it's going to stop 1 before the second. Now, if we look here, we could use our Shift tab to learn a little bit more, and we'll see that range has another argument, start, stop, and step. This is very similar to how we were using the slice function, where we were stepping every other or every third, and we can do the same thing. So here we're going to create a list that goes from the elements 2 through 10. So there's going to be 8 elements total, and it's going to be using every other one, which gives us, that's right, 2, 4, 6, 8. Which range do we appreciate? This range, this range. You can tell my cheerleader days didn't go too well. Now we can also go backwards. So we can have list range, and we can have 0 through -10. And remember, this is going to go around a loop. So what do you think is going to happen here where we have a -10 and a -2? Because before we talked about negatives looping back around in a list, but we haven't even created a list loop yet. So what do you think it's going to do? Well, let's find out. Interesting. So, -2, -4, -6, -8. Who do we appreciate? Yeah, it doesn't really work the same. But it is stepping backwards, -2s, and it is giving us a total of -10. So you can see it works about the same way. Now, interestingly, we can put positive steps and it's not going to be able to go anywhere because it's going to only have negative numbers for its list. So we have to have negatives for here and negatives for here if we're looking to step through a negative range. That's all. Range in a nutshell. Very powerful, very cool, very fun way to make lists. I want to touch on the power of lists when they're holding integers and floats and numbers we can work with and thinking of them as multiple dimensional arrays. So we might have something like this, a matrix, which is really a list of lists and it has nothing but numbers in it. It's got two elements, this element and this element, and each of those elements is a list of 3 items in themselves. But another way to think about it would be in a multi-dimensional sense. So we could actually think of a y and an x-axis and think of it as a 2D array where we have these numbers stacked on top of each other just like a matrix. And one of the things we can do when we start thinking about lists in this way is we can do things like rotate. So here, if we take the matrix, and we'll use this function that we haven't talked a lot about called zip, which combines 2 different elements together in a special way, and we reverse them by using the negative side of the matrix reverse that we talked about earlier. So we can actually output this, which is a different arrangement of the matrix that we started with, where 4 and 1 are grouped together, 5 and 2 are grouped together, and 6 and 3. But then if we break these out also based on the comma, the same way we did up here, you'll notice that it creates a different shape, 4, 5, 6, 1, 2, 3. 1, 2, 3, 4, 5, 6. It looks like what we've done is just rotated this around and we have a different shape now. And that's exactly what we did. We rotated a matrix. So imagine like in a video game when you want to move a character around or you want a character to like turn to the right. This is essentially the concept. Pretty neat stuff really when you start thinking about it. Another thing we might want to do is flatten them out. So let's look at some examples of that because there's a bunch of different ways to think about this. So let's start with a multidimensional array. We have 1, 2, 3, 4, 5, 6 on separate things. So another way we could actually write this out is using commas and spaces, and this is totally valid. We can run this cell in the exact same way we could have when it was all flattened out. Anytime there is a comma, feel free to drop it down to a new line, and Python will know to keep these all oriented correctly. And one of the things we can do is run this sum function over it, and for the second parameter, put a blank list, and look what we get. We get it all flattened out. 1, 2, 3, 4, 5, 6, all in one way. Now, there's a couple more complicated ways to do it. I just wanted to show you. We haven't covered these things, but using list comprehension, we can do it. There's also something called itertools that can do the same thing. So a bunch of different ways. This is the simplest. So thanks for watching, and let's get our right brain ready for another lesson coming up next. Subscribe to the Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations. Welcome. In today's lesson, we are going to be learning the how of programming by reviewing code examples that demonstrate tuples, what they do, what makes them different than lists, and what it means to be immutable. And then we're going to talk about a different type called sets, and how sets are a lot like a Venn diagram. They have the ability to calculate union, intersection, or difference, or even symmetric difference. So get ready, because these are a couple fun types to play with. Let's get started. So let's start talking about tuples. So tuples are very similar to lists. The main way you can tell the difference is because of the brackets on the outside. The circular brackets mean that it's a tuple, the square brackets mean that it's a list. And the difference is being that the tuple is unordered and immutable, meaning it can't be changed. And we'll talk about that more in a second. But let's start by just creating a list and creating a tuple so we can compare the difference. So when we run these first 3 cells, you'll see that even when they're printed to the console, they have the different bookends. So that's one of the easiest ways to tell what we're dealing with. Also, of course, we could simply ask by using one of our favorite functions, type, and noting that it's a tuple also. Okay, now let's look at some of the methods that are going to come with tuples. So let's use our trusty .tab function here that Jupyter allows us to do to see what methods a type has. So by hitting period and then hitting tab, I can see that a tuple has 2 methods, count and index. So here's a question. Before we look at those, what do you think is going to happen when we do a .tab on my list? Do you think a list is going to have more or less methods? Whoa, tons more, right? Okay, so the reason why there's so many more is because of an important property of tuples, and that is that they are immutable. We can't have an immutable tuple that's pointing to a mutable element. So there can be some changes, but on the highest level, the tuple is a secure, unchangeable thing. Now let's make a couple tuples. Let's make some DC villains because they're immutable. You wouldn't want to get rid of them, and then an integer one for pi. So one cool thing is that we can cast these into lists. We want to maybe edit these, but they're immutable. So what we do is we can take pi, we wrap it in a list function, and then we end up with a list. We can actually wrap this list inside of a tuple. So new list, tuple, and it's going to become a tuple again. So you can see now it's locked into place here. And finally, I just want to show you that just like the list, we can use the for loops, which once again we haven't talked too much about yet, but we can use logic on individual elements in a sequential order. One of the easiest being simply printing them out. So 1, 2, 3, 4, 5. If you know lists, you know tuples. Time to talk sets. Sets are very powerful, and they are different from lists and tuples because they don't have duplicates and they're not stored in order, and they are mutable. So I think of them kind of as Venn diagrams, like the same way you could imagine a Venn diagram using unions or intersections or differences. That's usually the way that we're going to work with sets. So we'll show some examples of that after we get the syntax down. The main syntax is to use these curly brackets on both sides. So you're probably noticing the pattern here with the square brackets for lists and the parentheses for tuples, and now the curly braces. Actually, the curly braces are used for both dictionaries and for sets, but the difference is a set only has one item in between the commas. Main thing to notice is that it has the curly braces here. So let's make a set. There we go. We've got Dylan, Elmer, Guillermo, Jen, and Naomi. So what type is this? Well, it's a set, like we said it would be. Now there's also a function for creating sets, and we can pass in a set or we can pass in a list, but of course we can't pass in the elements in the same way we would a list. It only takes one argument. The argument needs to be made up of several elements. So just for an example, we can see the function create sets in both of these situations. Okay, so now let's talk about the duplicates, because that's one of the big things about sets, is that in this list we have the number 2, 2, 2, 2, and that's just fine with a list. We can have a whole bunch of duplicate elements. It's going to remember them in order in a sequence. But a set does not. It can only have the element one time. So we're going to make this list a set and see what happens. We're making my list with the duplicates, and then we're passing that into the set function to make it a set. So when we look down here at the length of my list, when we check the length of this original one and we check the length of my set, you're going to notice that they're different sizes because it's eliminated all of the duplicates. In fact, if we actually want to print out my set here, you can see that it's now 1, 2, 3, 4, 5 instead of 1, 2, 2, 2, 2, 3, 4, 5. And now I want to talk about what we would do if we had a list of strings. So here we have a list of strings that we're turning into a set. Now remember, the dot split method is going to take each word and separate it by the space and make it a list of strings instead of one long string. So we can think of this as inputting a string for my, a separate string for peanut, another string for is, and then turning that into a list, which is then turned into a set. When we do that, I want to show that it does consider the difference between capitals, separate, and unique. Elmer, my, and is my is coming in as a separate character. And this makes sense. The Unicode behind the capital M and the lowercase m are separate, so it sees these as totally different elements. So even though it might read the same, we have to remember that something like a capital might be seen as different and unique to the computer when it makes the sets. Enough with the Venn diagram stuff. Now let's talk unions. So to take the union of two sets is as simple as calling one of its methods. Now we're going to need two different sets to work with, so let's take the first one again. My peanut is named Elmer. And then let's make another set, which is just names. But one of the names happens to be Elmer, so you'll see Elmer here and you'll see Elmer there. Now we know that sets can't have duplicates, and when a union is checked, it's going to see if there's any duplicates between the two different sets. The way this would work is we can pick either one. We'll start with names, and then we do .union to access the method, and then we pass in the other set. And when we do this, we will get a return that has every single unique element in either set. So we're combining the two. Now something like Elmer that's in twice is still only going to show up one time. but anything that's in either of the sets that's unique is going to make it into this super master list. So you might want to use something like union if you're combining two databases together and you say, okay, like you've got a big list of names and I've got a big list of names and we know some of them are duplicates, so let's push them together using the union and it will create a list of everything in both lists, but not duplicates of any, so we don't end up with two of one name. And just to show you, we can actually do it the exact opposite way too. So Peanut, because it's also a set, is going to have a method union, and then we can pass names into that one. And either way we do it, we're going to end up with the same list. Let's talk intersections. So very similar to how unions worked, we have methods that allow us to do this. And then we simply do names dot intersection, access the method, and pass in Peanut. You can remember from high school math, do you guys remember what the intersection is going to do as opposed to the difference? Only Elmer. I don't know if you guys expected that. If you did, kudos. Good job paying attention in high school. But the reason we got that is because the intersection is the only place in both lists where the same element shows up. So we have Elmer here and we have Elmer. And once again, just remembering that the reason why these look similar is because we're using this dot split to break this up. If we do the reverse, do you think we're going to get the same thing? Yep. Either way you do an intersection, it's only going to bring you the things that overlap specifically. So once again, if you have a big database and maybe you want to say, gosh, I wonder what in our database is overlapping, like who's signed up for your website and has also signed up for mine, you could compare email lists or something like that. So intersections are powerful. Now let's talk difference. This is a really powerful way to think about sets. So we'll make our traditional sets again, our Peanut and name set. Now what do you think is going to be returned when we do peanut.difference for the method and then we pass in names? Is that what you expected? Because I remember this one tripped me up when I was even writing this. It took me a second to remember what the difference actually was. But just like when you're doing subtraction, you have to remember that, say, 3 minus 5 is actually negative 2. You have to think of the first one as being sort of like the staple to compare the next one to. It does matter the order that we put these in. So names.difference and passing in peanut is different than peanut.difference passing in names. So here the way to think about this is that we have Peanut, and it's a set with all of these elements. My Peanut is named, and what it's going to do is it's going to bring in another set, and it's going to check if anything overlaps. And if it does overlap, it will be removed. So it found Elmer in the second set that was passed in, so it removed Elmer from the first set. And we ended up with something that was close to, my Peanut is named, and then there's no Elmer in here, and Elmer, which has been removed again, is my name. So you can see here we have everything that we had inside of Peanut, except it's now missing Elmer because that was the one word that was overlapping in the other. Just kind of think through the logic. You sort of know what's going to happen here, but it might not be instantly recognizable. So in this one, we're going to get all of the names minus Elmer because Elmer was the only one that was in the Peanut set. Tons of use cases for that too if you're trying to say like, remove all of these things from my database or something along those lines. Now let's talk about symmetric difference, because this is the one that is a little bit more intuitive for me. This is the one that just says subtract everything if it's in both lists. So we can do names.symmetric difference peanut or peanut.symmetric difference names, and we end up with the same result. We have a list here that just removes anything that's duplicated like Elmer, but it does combine everything else. So we do end up with names like Guillermo, and we do end up with words like peanut that are only in one or the other set. And then, of course, just to prove that it works, we'll look at it in the reverse. So, very cool. Now we know how to work with sets. We can do all of these unions and intersections and differences and tuples and their immutable states and the difference between lists and all of that. So the only thing left for the basic group types is the almighty dictionary. Get ready. We're going key value pairs in the next lesson. Subscribe to the Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations. Welcome. In today's Left Brain lesson, we are going to be learning the amazing powers of operators in Python. So we're going to start with the traditional arithmetic operators, a lot of the ones that you're already familiar with from your math class and from your math tutor, and then some gotchas. Then we're going to look at the comparison operators, which are the equality ones, greater than, less than, equal than. Then we're going to look at the assignment variables, a very important thing that we're actually already familiar with, whether we knew it or not. Next, we'll be looking at the identity operators to find out is or is not something what it says it is. And taking that a step further, afterwards we'll look at the equality, which is similar but a little bit different, and you'll see why. And then we're going to talk about membership, whether something is in a group or not in a group. And then finally, we'll look at logical operators. Let's start by talking about arithmetic operators. So pretty basic. The ones that you learned in math class, you're probably going to know, but let's just review them. So blackjack is going to be set to 21, Jackson to 5, and lottery to 0. So let's do some Q&A. What is blackjack plus Jackson? Correct. What is blackjack minus Jackson? Close. Yep, 16. Correct. What is blackjack divided by Jackson? Thank God I don't have to answer these. What is blackjack's times lottery? Yeah, 0, because anything times the lottery is 0. It's a losing proposition. Ooh, not defined. What are you missing here? Jabba-black. That would make sense. Looks like I didn't spell it right. That's going to raise it to the power, so everything that uses exponentiation, even if it's 0, ends up being 1, because that's how exponentiation works. Makes sense. Okay, and finally, let's talk about why the square root looks so different. And that's because we don't have a built-in Python operator for it. I mean, we do. It's part of the library that comes with it, the math library, but we have to remember it's not quite as easy as just using one of these operators. We have to actually bring in the module math, and then we have to call the method sqrt and put our variable in there. So we can still do it. It's not impossible, but just know it's a little bit of a different route. And I can understand that not everybody had the greatest math teachers, so maybe sometimes you had to learn a little bit more arithmetic from your tutor, so let's go over those. And just in case you need a refresher, the double whack, which is kind of the Urban Tech Dictionary version for a / a whack. Blackjack, whack, whack, Jackson is no remainder division, meaning we will end up with what? 4? Did you get that? So we have 21, we have 5. It's going to go into 21 4 times evenly, and then we're going to have the remainder of 1, but we just throw that away. Okay, so double whack division means we throw away the integer. Now, mod using, and it's hard to get your head around, but it's kind of like when you ride a bike, you never forget once you see it. Okay, so what do you think we're going to get when we use the modulo operator on the exact same problem? Blackjack, modulo, Jackson. Did you guess 1? Well, maybe not, but I bet now you have a sense for it, right? Because the 5 is going to go into the 21 4 times with a remainder of 1. So it's like getting the remainder only. But just to sink this in a little bit more, it's interesting to think about what's going to happen. So let's try it again. 10 modulo 1. Well, we know 1's going to go into 10 times and nothing's going to be left over. So maybe we're going to get a remainder of 0. Right, nothing left. What about 2? That goes into 10 evenly also. Do you think we'll get a... Yep. What about 3? Now we know 3 is only going to go into 10 3 times, and we're going to have a remainder of... okay. 5 goes in, yeah. All right, I can see it. Ooh, 10 goes into 10 just 1 time, no remainder, maybe 0? Correct. Uh-oh, now we're backwards. So now we have the bigger number on the right, or the denominator. And what do you think happens here? Because it can't even fit into it 1 time, let alone have a remainder. It just gets stuck at 10. Interesting. What if we go even higher? Do you think it's always 10 no matter what the number is on the other side? Yep. Those weren't really questions. I gave them away. But now let's look at some gotchas, because that's where things get tricky. All right, dividing any 2 integers will produce a float. So we talked about earlier how you want to save memory by using integers when possible. And if you're casting them and it's happening automatically, it's called coercion. So 9 divided by 3.0 and into a floating number is going to give you a float. But if you actually have 2 integers and you divide them, you still end up with a float. So that's another important thing, is you can't actually keep integers even if you're doing perfect integer math. It just does this by itself. So you would want to wrap this in the int function, and then it could take the answer and do that for you. There's also a 0 division error that we need to be really careful about, and this has definitely broken every one of your calculators in elementary school, but we get the same thing. And we're going to get this kind of an error, zero division error. At least we know what's going on when we see the error, but you know, even Python's not powerful enough to divide by 0. And now let's look at some comparisons. 3 is at less than 10. We're going to get a Boolean value returned, a true or a false. True, obviously. Okay, so here we are at the movie theater. You've all seen the pricing. It's terrible. It's $1.50 if you want a small popcorn, $3 for a medium, or $18 for a large. Set some variables and do some single comparisons. Is small less than large? True. Is small greater than large? False. Is small greater than or equal to large? 150 or 18? Nope. What about less than or equal to? False. Okay, so just look at the syntax there. If you want to do blank or equal to, use the symbol and then use the equal sign right after it. Here's one gotcha warning, is it can be really easy to just do that backwards. Like you put the equal sign first and then you use the greater than or less than operator, and you will get a syntax error for that. So just a little reminder there to make sure to use the greater than or equal in the order that you would say it. Greater than or equal to blank. Okay, done with that. Let's look at multiple operators. So this is kind of where it becomes powerful, sort of more powerful than your regular calculator, is you can just start stringing this stuff together and making it more and more complex. So we can use the word and. We're going to learn a little bit more about that later, but is small less than medium and is medium less than large? That is true. Is small less than medium and is medium less than large? You tell me. True. Is small bigger than medium and is medium less than large? False, right? Small is not bigger than medium. What about small being less than medium and medium being less than or equal to medium? Yes. Small equal to medium. Well, we haven't seen this yet, but double, you're going to see this is an equality operator. And the double equals is saying, is it exactly equal to? So remember, the regular equal sign, that doesn't work. That's what gives us an assignment. So double equals is saying, is small exactly equal to medium and is medium less than large? False. Okay. I think you get the picture. Now let's look at a little bit of mixed up stuff, because we can do some arithmetic operators right in the middle of these comparisons. So imagine small plus small plus small, that's $1.50 times 3. Is that going to be, once it's totaled, less than the medium of $3? And is the medium going to be less than the large? False, right? Because this totaled up to be more than $3. $1.50 times 3. What about when we throw the parentheses around it? Okay, so now we have small plus small, and then we're going to multiply it by small. Then is it going to be less than medium and less than large? Take a second. False. What about if we do is small less than medium or is small less than large? Or is a little bit different than the and, so we only need one of these to validate to true for the whole thing to be true. And of course, it's true. So there you go. I'll give you a little overview of the way we can use the comparison operators. Now, probably the most powerful one that we've already used a lot, next up, is the assignment operator. We had to learn the basics of the assignment operator early on. We needed it just to work with variables, the equal sign. But there's a lot more to it than what we know. And there's also some great shorthand notation. And in fact, the many things the assignment operator can do also mimic the story of my life. So I thought this would be a great time to tell you that story. Story of my life. First, I was a fetus. It's much weirder to say out loud than it was to write. And then after 9 months, I was born. And in fact, actually, I was 0, because that's more Pythonic. After 9 months of being a fetus, I was born 0. And then I had my first birthday after 12 months of being alive. That's more like how Python would do it, so that's why I'm going to do it. Then, after 79 more years, I became a grandpa. So this new variable, Dylan, is assigned the old variable plus 79. The old variable is 0, so we're going to have a Dylan that is 79 years old. But then I found an expensive lotion, and it took me back into my tweens. Now note the difference on this line, because instead of having to assign it to the old variable plus that variable, we can just squish the two together in this nice notation, and it's the equivalent of subtracting 65. There I am, 14 years old again. Awkward years, here I come. But then, after twice that amount of time, the multiplication, I found love at 28. Identity operators are really powerful, and I find them easy to understand in the terms of just simple English. Okay, so we have is, right? Bip is equal to bippity, bop is equal to boppity. Bop is bip. It's kind of saying like, are these the same? Is bip equal to bop? False. What about bip being equal to bip? True. And what about if we use the is not? So it's just as simple as saying, is bip not equal to bop? Kind of. But in that term, in the syntax of is not in the way I said it. And you get a false and a true. All right. Well, there's cool ways to mix and match this too. So we can say, is 3 3? True. What do you think about this one? Is 3 3.0? We know they're different types. False. Okay, so we know that even if they're the same number, if they're not the same type, it's not going to work out. What about true is true? Is that even valid? Okay, I guess that's true. What about true is false? Ooh, it's like a conundrum. False. Okay, true is false. I guess that would be false. What about false is false? Could that be true? Yep. Guess what? False is false. So, it's true. It's true that false is false. Two wrongs in this sense make a right. What about false? Just period. Okay, false. You have to remember, it didn't really need to return this. Like if we... it returned false because it's actually something that returns a Boolean value because it turned out false. What about not false? Yeah. Oh, true. Okay. So there you go. True is true. True is false is wrong. False is false. That's the same. False, false. Not false, true. All right. Super, super simple right there. Easy to understand, huh? Might have to wrap your head around it for a minute, but that's how identity operators work. Let's talk equality. Everybody, we need to be more equal in this world, especially you stupid popcorn prices. Okay, so here's what we got, something interesting to pay attention to. Double equals. Now, the weird thing about double equals in programming is that it's not the same as equal. It's not an assignment, and it's much more like what you would think of as the normal equal sign if you weren't a programmer, like what you learned in school, like is this equation equal to this other equation? That's what we're asking. But we use a double equal sign because there's also a way to write it like is not. It's kind of a more sharp way to have two of them so we can combine them with the exclamation point. So just kind of remember that it's going to feel a little unintuitive to use double equals for is it equal to and the regular equal to for like become this, the assignment operator. But just so I can show you how it works, small, we're asking is it equal to large, and we're going to get back a Boolean response of false. But if we ask, is small not equal to large, which we know it's not, we're going to get a true. And then just a little gotcha here is you don't actually get thrown a warning if you do it backwards, but it doesn't work. So it can be a place where a bug in your code comes. You see it's like, yep, worked for me, but nothing really happened. Not in this sense. Not in the sense we're trying to use it for this Boolean response. Okay, so just make sure you always get it the right way. And it's similar to when we used the comparison operators. This piece has to go in front of the equal. Okay? And that's equality. Now let's talk about memberships. Obviously, everybody wants to be a member of a cool kid group. So what if 34 is not in the cool kid group? How do we check? Well, we can just say, is 34 in? And then we have this list here, which we'll talk more about in the next video. 34, 35, or 36. If the answer is yes, give me a true. Yes. Okay, and we can also do with sentences. If the word good is in this sentence, this is a great example, then give me a true. But it's not, so we get a false. How about this? What about if good is not in the sentence? This is a great example. It is not in this, so we'll probably get a true. So I think you can see how it works. 34 can also not be in a group, which is false because it is in the group. So I kind of give you a quick overview of how the membership operator of in or not in works. And last but not least, our good old Spock logical operator, one of my favorites, because it's right there. It's just in your face. It's not going around the bush. It's just boom, true or false. Give me a yes or no answer, Logical operators got things to do, places to go. So cat equals true, dog equals false. Cat or dog. So what we're saying here is true or false. Are either of them true? Yep, cat's true, so true. Here we're saying cat and dog. Are both of them true? Well, we know they're not. We know dog's false, so probably false. And here we can wrap it in a little bit of an if statement, something else we're going to learn about more, but this is very cool because it gives us the power to say if true, then print high. And if false, well, don't print high, which is the equivalent of nothing. How about if not true? You might be getting a hang of this now, but if something's not true, then it's false. So nothing happens. If something is not false, then it's true. So something happens. Okay, so we get the print of high. And just to close it out, here's a little bit of a way you can imagine putting things together to create some more kind of advanced functionality. Let's assign a and b both to the variable 5. And then let's ask this question. If a is equal to 5 and if b is equal to 5, then print, we're both 5s. And they both are, so it's been printed. And we can also use it the other way. We can say if a is not 5, okay, which it is, so that one's going to come out false. Or if b is equal to 5, I'm going to change that right now, and we're saying that this one's evaluating to true, so either this one or this one evaluates to true. This one's false, this one's true. Then give us another print. Boom. One of us is not 5, which is also true. Subscribe to our Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations. Okay, in today's lecture, we're going to be looking at some examples of conditionals. So we're going to look at a canonical example to start with, and then we're going to get an overview of the keywords if, else, and elif, and then we're going to look at how they can stack into decision trees. We'll look at some ways you can write them out in one line, and then when you have more complex logic, how you might want to look at nesting them and how those will evaluate. And finally, we're going to sort of mix and match these conditionals with things that we've learned before. Okay, we are back now with our trusty Jupyter Notebook. So let's look at a concrete example of a conditional. So look at this variable. We have taste, and it's equal to the string good. And we have calories, which is becoming the integer 350. Now we can use these in almost an English readable sentence. Print the string eat cake if the taste is equal, the double equal sign, to the string good, and the variable calories are less than the integer 300. Else, print order salad, right? So, can Elsa eat a cookie if she walks up, thinks it tastes good, and has 350 calories in it? Nope, because that's too many calories for her variable. It says that it has to be less than 300. So, instead of printing eat cheesecake, we got order salad. Okay, so let's look at all the different keywords that we have and how they might kind of bunch together. So, if you remember, is represented by Anna. Now, if calories are less than 300, what do you think is going to happen without anything else specified? Nothing. So we executed the cell, absolutely nothing came out. However, if it would have hit the Boolean true, we would have got an outcome. So that's one thing to remember, is that nothing else happens by default. You have to actually add this else statement, which of course is represented by our mnemonic for Elsa. And in this case, it's not going to validate up here as true. It's going to come out as false, but then it's going to say, if that's false, then do this. And then, of course, we can put the third one together, which is the elf, who's sitting in between the two. And if the calories are less than 300, print eat. Else if, kind of in English you'd say if else, but calories are exactly equal to 350, print just this one time. Else, print order salad. Now, the cookie is 350 calories, so what's going to happen? Correct, just this time. So, got away with this one because it's exactly on the dot. Now let's look at decision trees. So, that was our mnemonic with our kind of dead tree with no leaves on it. We have a couple variables here for Elsa and Anna set to 21 and 17. Now, we're going to find out what fun things Anna is old enough to do. Now, if Anna's age is greater than or equal to 21, print she can drink and drive. Of course, but not at the same time. Very, very important you realize it, not at the same time. Else if Anna's age is greater than or equal to 17, and Anna's age is less than or equal to 21, we can print she can drive but not drink. So using that and operator, we've now specified that we have to be in between 17 and 21. It has to be inside of that bracket, that range. And else, we can print she's not old enough to do anything fun. So Anna's 17. Why don't you follow the logic through here and see what's going to happen. All right, well, let's first assign the variables to their respective ages, 21 and 17, and she can drive but not drink. Man, that's 17 for you. It's a sucky time in your life. All right, let's talk about some simple logic and how we can kind of code these things both in one line or in sort of a more spaced out way. Now, Python can handle tons of conditions, but how you want to write them is important because you have to give your code to other people, you have to read it yourself. So let's look at a couple one-line examples. Now, to me, this logic's pretty readable. Print kid if else's age is under 13, else print teenager. So what's going to happen? Elsa we just assigned to being 17. She is a teenager. But this one's a little more tricky. So we have two if statements in it. Print kid if Anna's age is less than 13, which we know should print else because it's a teenager. But then teenager if Anna's age is less than 18, else adult. So what do you think is going to happen? First evaluate here and then there, or there and then there? Take a guess. Teenager. Okay, let's look at this in a more spaced out way. So we've talked about it before, but Python, of course, is aware of white space. This is what saves us from all those terrible brackets from other programming languages. But the important thing is that they represent a sort of nesting that you can't quite see here as well. Now, if you look at this, if Anna's age is less than 18, then if this evaluates true, go into the block here. But if it evaluates as false, just skip that whole block and go down to here. And then once you're in here, you're going to then look at the age to see if it's less than 13 to print kid, else teenager. So take a guess as what this code's going to run before I hit it. Teenager again. Okay. So the thing that's important here is that this evaluates in kind of a different order. So Anna's age is less than 18 is now here on the back end. And you can think of this as coming first, not as something that comes first in one line, but as something that's inside of this thing. So the thing at the end is actually the biggest because it's like, I'm inside of this thing. And you can see that much more clearly down here. But over time, as you learn to program, you'll see it kind of compressed into one line more because people are starting to save time and kind of type more advanced. But at the beginning, think of it like this until you've got it kind of in your head how it works. Now imagine this. Two-Face has captured Batman and he happened to come in. I don't know why he's at the bake sale or with the Frozen guys or whatever, but here he is. And he says to Elsa and the elf and Anna, hey, I've got Batman here, but there's a chance he could survive because I'm going to flip this coin, and it follows this very special logic. If not true, print Batman dies. Else print Batman lives. What do you guys think is going to happen when Two-Face flips the coin? Batman lives. Of course he does. He's Batman. Let's talk about why. So, if not true is kind of a weird statement. Now, let's just look at if true. Hate to do this to you, Batman, but now you're dead. Okay, so if true is the Boolean answer we would have got if Anna's age is less than 18. We would have actually got back from just this chunk of code there either a true or a false. But you can see you can actually skip the processing step and just type it right in. So if true, do this. If false, do this. And then the kind of the trickiest one, and you just sort of got to think about this for a second and make sure you know it. If not true, that's false. Why not just write false? Because it's wordy. You should, but just no. If not true is the same as false, and that's why you end up with Batman living. Okay, last thing. Let's go look at a few ways we can sort of mix and match these things together. So a reminder that we have the taste set to good and the calories to 350. Now, what's going to happen here? Print eat if taste is good and calories are less than 300, else order a salad. Calories are 350. Order salad. Right. All right. Now, how about this? What if Elsa says, hey, you know, I know there's 350 calories in there, but I'm going to exercise right after this, and that's going to burn 200. So now let me see if I can eat this piece of cheesecake. And you can see that we're actually doing the math here. It's in the parentheses, so it should be executing first, and then it's going to go and do the rest of this statement. So what do you think we're going to get? Ah, she gets to eat the cheesecake, even though it's over calories, because she burned some off. All right, and now finally I want to just talk about what we do when with the operator for memberships is added. So now the taste isn't good anymore. The taste is awesome, but the calories have dropped, so it should be edible. What's going to happen here? Print eat if the taste is in the list with items, awesome, delightful, and delicious, and the calories are less than 300. Else order salad. Awesome. Is it in the list? Yes, it is. Nice. So awesome is right there. But if it was good, that would be no good, because then you would have to order salad. Thanks for watching another video. I will see you next time. Remember, be smart, be creative, and be syntactically observant. Subscribe to our Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations. Welcome to today's left brain lesson on loopies. I mean, you know, loops. Sorry, that was lame. We're going to start with learning about for loops, probably the most common type of loops, and then we'll look at a cool thing called enumerate, which we'll use all the time to keep that stuff in order. And then we're going to look over what kind of types inside of Python we can even loop over, because at first you don't really know. Strings, range, lists, dicts, who knows? And then we're going to look at starting and stopping within loops. So sometimes you want to break out of a loop, something changes, you're done with it. How do you trigger those kind of things? Then we're going to look at a while loop, very similar to a for loop, but it's going to work on a different type of conditional. And then we're going to look at nesting. So can we have loops inside of loops? It's very, what's that movie called? Inception-y, kind of. Loop Inception. And then we're going to look at a really fun thing. Ah, heck, this is so fun. I'm just going to show you now. We can use a loop to, boom, make a status bar. It's going to get, you know, see how far through the process of looping we are, which I just think is the coolest thing ever, and we can do that by only importing one module. So stay with me. You're not going to want to miss this episode of Looping the Lesson. So what do you think is going to happen when we take this variable food, that's a list, and we put it in this syntax? For, and we just make this word up. It doesn't always have to be item. It can be the letter I. Sometimes you'll see it as the, like, you know, food. This will be like foods with an S, and then this one will be like food without an S, something like that. Of course, then we have to run this whole thing again, but why not? Let's just do it. Foods, food. Oh, there it goes. That's what you get. You get pizza, pasta, salad, nacho listed out. So what we're saying here is for food in foods, print whatever this thing is, okay? And it's a great way to just name things in a way that you understand, and to understand that this, as long as it's a list or a type that can be looped over, that's all we have to do. So what do you think is going to happen when we add in one more thing called enumerate? We're going to wrap this function around our foods. Oh man, am I going to have to fix all of these? Okay, around foods. Is that what you expected? Very powerful, very important function that we can wrap something that can be looped in is called enumerate. And this allows us to create both an index and an item. And we can print out the index, meaning how many times the loop itself has happened, and the item being the place inside of the loop, the list or the items that we've passed into it. Excited about for loops, like, you know, you're thinking about all the cool stuff you could loop over, and you're probably thinking, but what stuff can I loop over? Who can tell me that? Well, I can tell you that. Let's look at different things that are commonly looped over. For instance, strings, might not have thought it, but check this out. The string hula hoop can just be passed into that same syntax for item in and then the name of the string, and we can print out the item. hula hoop, and it's going to create something where each character is its own item, because we talked about it before. Strings are kind of like lists in the behind the scenes. Now, what about this? Remember the range? Wait, have you seen range? You haven't seen range yet, so check this out. For I in range of 20. So what we're saying is create a list of 20. Depends on how deep you went into the concept of types, if you saw range or not. But, so you know, they're basically just like a list. Think 1 through 20 of a list, and boom, there it is. You can do cool stuff with it. Okay, so what about jumping over a gap, okay? So don't worry if you haven't seen this thing yet, but this is another range, which is a list, but it's going to skip every 2. So actually, the reason I like this in particular is that it goes 2, 4, 6, 8. You know, 2, 4, 6, 8. Pretty cool, huh? So we know we can loop over strings and ranges, and we actually already know we can do lists, but just to show you again, to keep it in context with everything else, we can make a list, our bucket list in this case, and then we can just print out the things that we still need to do before we die. What about dictionaries? These are where it starts to get really powerful and a little complicated, so stay with me here. We created this dictionary called Colors, and it's got 2 items per dictionary, a key and a value, as we talked about before, and we can loop over it in the same way. And the first item that we do is going to always be the key. If we only put one kind of argument in between the for and the in, then we will get the keys, the first part of the dictionary. We can also get the values, right? By putting k, comma, v in colors, and then we use this dot items method at the end. Okay, so a few things to remember here is it doesn't matter what letters we're using here. Like this is not going to work. Okay, I mean it's going to work in the sense that it's going to print out both, but it's not going to print out just the key. And if you're wondering why it didn't just print out the key this time, it's because we're using this items. If we did that, we would get just the key. All right. Hopefully that is clear, and now you know that we can use dicts, lists, ranges, and strings in loops. Another way to construct a loop is called a while loop, and these can be useful in the right situation. So it works like this. We start with a variable. In this case, we're going to make a bunny hop, and we're going to say that we want it to hop 3 times. And we construct the loop in a way that instead of using for, we use while, and then while hops is greater than or equal to 0, then we're going to print hops. And then after we've printed it, we're going to decrement it by 1. That way, it eventually comes to an end. So we get 3, 2, 1 hops. We can do the same thing with something like temperature. We're going to say while the temperature is greater than 112, then print the temperature and then decrement it. And notice this time we're using the shorthand. And we can say, oh, the tea is now cool enough to drink. It wasn't when it was 115, but it is now at 112. So here's a question. Can we count up also? Of course we can. If we can decrement, we can increment. And that can be useful in many cases when we want something to just happen a certain amount of time. You know, we don't always have to have like this 9 kind of hard-coded in either. We can say like, you know, check a database, see how many students in a classroom we have. That number turns out to be 32, and then just put that variable there. So then it will count up just as many times as we have, you know, students in the classroom or something, and we don't need to actually construct a for loop and have that data in exactly the kind of format that Python can loop over. So you can see the advantages. Let's look at breaking out of these loops. So there's going to be times when we don't want the thing to just run X amount of times. We want it to check some kind of a condition, like should I still be doing this, or has the goal of this loop been accomplished and it's time to stop. So let's start by just placing a conditional inside of a for loop and show you what that looks like. All right, and don't let this character throw you off. I just thought it'd be fun to go get another, you know, UTF-8 icon so you guys would know how fun Python can be. So in this case, we're running a range. So it's going to run 6 times, and it's going to ask if this Captain Picard icon is 3. Print make it so. Else, print not so. So this is what we get. Not so, not so, not so, make it so, not so, not so. Pretty cool, huh? So you can see that it's just running through it, and then when it found the one that was equivalent to 3, because we used our is conditional, then it said make it so, and it was made so. And the Starship Enterprise survive that encounter. But here comes another encounter. Will Captain Picard make it so this time? For Captain Picard in range 6, if Captain Picard is 3, then print make it so, but then we're going to break out of the loop. So we're not going to get to the rest of them. So will he make it so? He will, but he's not going to make more not-sos afterwards. So this break, kind of as it seems like it would be, it just takes the entire loop and stops doing it. It breaks out of it. Okay, so we also sometimes might put the break before the print statement. So do you think it just it executes everything in this block of code and then breaks? Or do you think it's going to print something underneath the break? Well, let's find out. Not so. Okay, so we have to remember that when it breaks, it really breaks, like right on this line. It's not just breaking out of the loop at this code, but it's where it's specifically located. So, you know, that can be another bug in your code at some point. You might say, like, when I was breaking out, did I really complete everything I needed to complete? Because as soon as it sees that word, it's done, even if you're already in this block of code being executed as valid. All right, so enough with breaks, enough with conditionals. What about continue? That's kind of a weird one. We're in the, you know, the Star Trek deck with Captain Picard from the Next Generation, obviously the best version of Star Trek. Here's how it goes. For Captain Picard, I just wanted to use a Unicode 8, so don't let that scare you. You can use any letters you want or any word you want here, but I chose Captain Picard Unicode icons. So for Captain Picard in range of 6, if Captain Picard is 3, print make it so. Else, also make it so. So we got make it so's all over the place. How many times will Picard make it so? Yeah, 6 times. That's pretty obvious, but we're building up to stuff here, okay? Now, what if we wrap it in the enumerate? Now we have an index, so we can say how many times this is looped, independent of knowing exactly that this is a range 6. It's easy for us to see in this example, but a lot of times it won't be. And when we do this, we are going to have the same thing, but now we also have our index to help us keep track of how many make it so's we have. So far, Captain Picard's like making it so every direction, you know? Like, should we fight the Klingons? Make it so. Should we, you know, do something good for someone? Make it so. He's doing that everywhere. But now, all of a sudden, continue is into the loop. So when we get to the third part of the loop, the third iteration, and Captain Picard becomes a valid true statement because Picard is going to be 3, we're going to have to make it so and then continue. What do you think is going to happen? Psych, nothing yet. Ooh, even more build-up, you say, Dylan. More, you're building up more, and it's so intense. I don't see why continue did anything, because it doesn't do anything according to this example. Well, that's because it was underneath the statement. Now look, what if continue is put in front of print? What do you think is going to happen now? 1, 2, 3 make it so's, and 4 no make it so was made so? That's because continue isn't just something that applies to this whole block. It's specifically that line of code. And this can be where bugs come in sometimes in your code because you're like, I don't know, I executed it, it was valid, and then I continued, but it didn't happen. So it's actually something you always want to put, you know, down here at the bottom, like it is in this example. So in this example, it's saying if this and then continue, but there's nothing else to continue down here, so we don't see it. All right. So to make this really clear, what's happening is that when it hits continue, it's not breaking out of the loop. The loop is not stopping, but it is going to stop doing anything below it in its specific block. So this print statement never got a chance to be made so. It just went all the way back up here to the loop and then continued. But it never missed a beat. See, we've got the index here to prove that. 3, 4, 5, 6. It just didn't make it to this, even though that was valid. Okay? Well, that's break and continue for you. So now let's not take a break and continue on with nesting. Well, welcome fellow birds to our next section on nesting. Twerp twerp, or tweet tweet, tweet tweet. Okay, so I'm getting a little crazy in this room, but nesting is a very difficult task for a baby bird like you to learn. And it's my job as the mom-ish, actually the dad, bird to teach you how to build a nest. And I am going to do it in the only way I know how. I'm just going to throw you into the deep end. We're just going to push you out of the nest, and you're either going to fall to the ground and die, or you're going to learn how to nest. So we have a variable that's set to an empty list, and we're going to append a few things to it. Now, from the outer ring, we're going to be appending 1 and 2. And from the inner ring, the inner loop here, we're going to be appending 11 and 12. So I also put these in order of true and false, so you can see that it's this one, then this one. Now, there's no real good way to, I think, explain this. I tried a few times in rehearsal, but I think best just to print it out and let you guys look at it. And let's talk through it best we can. But it's one of those things that I would say keep staring at it, maybe pause your video kind of thing. So if you're ready, of course you're not ready. You're a baby bird. You don't know what I'm doing. But no sympathy. Got to push you out. It's for your own good. All right, you flew. Good job. You're a flying bird now. So let's see how you did it. All right, we have the very first thing that was printed, that was appended, is the 11. So it obviously read from the first ring first, and then it printed our true statement, and then it went and got our big stick, our first big stick 1. Then it did the next thing, and that was print the false version of the same small stick and big stick. But here's where it gets interesting. So now it moved up to 12 on the inner ring. It kept being true, and it kept the same position on the second loop. It didn't go all the way back. It just looped this one once, then looped this inner one twice. So you can see now it's got a false, but we're still on the first iteration of the bigger loop. And then once it was done with that, it finally went up to the bigger loop, and then it ran this, appended the 11, and then the 11 again, and then it went up to the second 12, and then the second 12. Okay, so I guess point is it's like loop, 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 doo-doop, doo-doop. So it'd be like 1, 2, 1, 1, 2, 2, like that. Make sense? Kind of tricky, but just play with it and get your head around it. Here's another way with a little bit more nesting, so you can see if we had a list that was already pre-made and it has single digits, double digits, and then triple digits. If we were to do a for loop, and then print out everything, you can see that it will print in sort of this pyramid order. One more thing to get you kind of thinking about how to do it is for I in range of 1 through 10. Okay, another for loop, which is X in range for 11 through 20. In this case, you're going to see that it's going to be pretty long, and it's actually going to print 11, 12, all the way up to 19, and then boom, back to 11, 12, all the way to 19, and then boom, back to 11, 12, all the way up to 19. And I think you get the picture. But guess what? All of this work was not in vain whatsoever, because we are now going to learn the coolest thing that you can do with a loop ever. That is watch your nest get built with a progress bar. Yeah, boop, boop, we did it. Loops are done. We have completed this lesson. Yeah. Subscribe to our Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations. Welcome. In today's lesson, we will be learning the how of programming by reviewing code examples that demonstrate how dictionaries work. We're going to talk about some of the most common use cases and methods, the basics of creating dictionaries, how to display the keys and values that are inside of them, how to retrieve keys and values, sort dictionaries, insert new elements, and of course, remove things that we don't want. Then we're going to talk about loops, something that we're not going to cover in detail here, but there's some very powerful ways dictionaries can be combined with loops, and I want to give you the first overview of what to expect in some of the later videos, and how the power of the two can be put together. And then finally, we're going to talk about default dict. Now, this is a special package that we can bring in that mimics most of the dictionary functionality, but also adds a few more elements that can be useful. So get ready for a good time with dictionaries. Let's start with the dictionary basics, creating an empty dictionary. Now we use the curly brackets, which is very similar to sets. So let me show you the main difference here is really in how we structure the data that's inside. So we use curly brackets for a set, and we use, in the example of strings here, we'll make the first element, and then we'll use a comma, and then the second element. But with dictionaries, we have to have a colon between the two instead of the comma. So if we actually wanted two dictionary elements, it would need to be two pairs. For example, something like this. That would be the equivalent of two items inside of the dictionary, whereas each item has a key and a value. So since they both use curly brackets, here's my question. What type is this variable going to be? A set or a dictionary, since we haven't specified anything with our format? Got your guess in hand? It's a dictionary. Not really sure why, but that's just the default that they use. So in fact, if you actually wanted an empty set, you would have to do something like that, where you created an empty bracket and then typecast it into the set type. The basics are the colon and the comma pattern inside of the brackets. Next, let's look at some ways we can display dictionaries. Because there's two elements, both the key and the value, there's a few different ways we can actually display them also. So let's start by making a dictionary that we can play around with. It's called Hogwarts, and it has the names of some of the Harry Potter characters, and then after the colon, it has the house that they belong to. Hermione is at Gryffindor, and Hannah is at Hufflepuff, and of course Penelope and Ravenclaw. Nobody likes Penelope. Now, just like we print all variables, we can simply do Hogwarts to see the entire pair. So we can see the key and the value. Now, another way that we can display the key and the value is by using this method called items. There's some more functionality with items, but nothing that we're going to worry about now. So most importantly, if you only want the keys or the values, we have separate methods for those. So Hogwarts.keys is going to return just the 3 people, and then Hogwarts.values is going to return just the 3 houses. So a few different ways to display those there. Now let's talk about retrieving elements out of dictionaries. This is something that comes up a lot. So we're going to create a new Pokemon dictionary here. And one of the main methods we can use is this .get method. And the method requires one argument that we must pass, and this pass is going to be the key for the value that we want returned. So we have to pass in either a string or number that matches one of the keys here. So you can see we have Arbok in here. We have Arbok right there. So we would expect it to return the value. Like in a real life dictionary, this would be like looking up the word here and then getting the definition back. When we run this, we will get 14. Now it doesn't work the other way. We can't put in the value and then get back the key. It doesn't work that way. Now there's also a shorthand. Without using the method .get, we can use our slicing. If you remember earlier, we had the 2 brackets and they were put right up against the variable here, and we can do the very same thing. So we need to pass in the key, which we have right here, and it will return the matching value, 89. You can see that we have 14 or 89. So now let's look at a second argument that the get method can actually take, and that is a return value if nothing is found. So in this case, we're going to look for Jerku. Oh, Jerkaku. Yeah, that's right. Kind of like Pikachu, but a jerk version. In this argument, we're saying, look through my dictionary, and if you find Jerkachu, then return it. And if not, return Pokemon not found. So in this case, we know that Jerkachu is not Ivysaur or Pikachu, Arbok, or Jigglypuff. So when we run it, we will get Pokemon not found. So now let's talk about sorting a dictionary, because inherently dictionaries are not stored in a sequential order like a list, but there are functions that we can wrap around them to get some of the functionality that we need. So let's go ahead and create a new Hogwarts dictionary with some of the characters and the houses that they're from. And then let's sort them. So first, we know the items is going to return both the key and the value. So when we sort these, we get everything returned and sorted by the key. It uses the key first. So we have HA and then HE and then the letter P. And then we can also specifically say sort it by the keys and only return the keys. And then we'll have the same thing, but we won't have the values returned also. And of course, we have the .values method, and we can run that before using the sorted function and get a similar result, but this time sorted on values. So you can see that can be a great way to actually sort out your dictionaries when the need arises. Now let's talk about inserting new items into a dictionary, new key value pairs. Let's start with our Pokemon dictionary here. We have our Pokemon and the level that they're at. Ivysaur is at 89, and Pikachu is at 11, and Arbok is at 14, and then Jigglypuff is over there at 51. So now I want to add two new Pokemon. My first one is Professor X, and he is at level 34, and my second one is the Joker. Now, we specify the new item in the same way we would slice out one of the values based on key, except we add a new one. So Professor X does not exist in the dictionary at all right now. This would normally cause a key value error, except we have an assignment variable here, and we're also giving it a value. When we run these, you can see that both the Joker and the Professor X have been added to our Poke dictionary. Right, and there we go. Now Joker and Professor X have both been added as keys and values. So our dictionary is growing. Now, let's talk about what we do when our dictionary gets too big and we need to remove something. Removing key value pairs from dictionaries can be pretty easy. So let's go ahead and make another dictionary with Poke just to remind ourselves what we have and reset it. And then we simply use the del keyword, and the same way we would slice an item out, hoping to get a return value, we just put del the keyword before it, and then all of a sudden, Poke Jigglypuff is gone. Now we just have Arbok, Ivysaur, and Pikachu. Another way that we can actually clear an entire dictionary is by using a method that all dictionaries have called clear. And when we do this, we end up with a dictionary of nothing. And that is removing items from a dictionary. Now that we have an understanding of the basic ways we can work with the dictionary, I want to talk about what we can do when we combine them with the powers of loops. Now, loops are an entire lesson that we're going to talk about in the section on recursion. So I don't want you to look at this and think it's stuff that you should know, but maybe take a more relaxed attitude towards this loop section. Just see some of the things that we can actually do with the dictionary when it comes to nesting and looping. Just to go kind of quickly over this, the same way we had the Hogwarts.keys and we could display the keys out, we can actually specify something called for and say for I in Hogwarts key. And this is saying for the index or whatever character string we want to put here, for I, or whatever variable we choose to put here, for I in Hogwarts keys. And we can actually print the keys. So we can just print the keys out. Now we also can do the same with values, and then this variable I will become not the keys, but the values. And we can also specify both a key and value. So remember, these are just variables. We can choose them to be anything we want. And here we can actually combine the two together for a custom combination. That way we can actually have a couple variables here that can be used together in all sorts of combinations using the .keys, the .values, and the .items. Now, like I said, you don't really need to know this right now, but the reason I put them here is because I think someday you might want to come back to these videos, and this seems like the most logical section to keep some of this stuff. So just like we were sorting things before by printing them out with the keys and values and then wrapping them in the sort function, we can also do that with loops. A little bit more complicated, but sometimes there can be more places where we can add new logic, so there can be reasons for it. But just so you see, it's the same thing. We're organizing by keys, but here we're using some different logic to organize it, but just another way to do it, just for your reference for later. So now something you should pay attention to again, the default dictionary. I want to talk about the default dict. It's a different type that we can bring in using a package. And the reason why it can be so powerful is because it allows us to specify some logic, saying if you get a key and you're not passed a value, instead of throwing an error, just use this as a default. And this makes it really powerful for quickly appending items into it that aren't completely validated ahead of time. So I'll show you with an example here. So we're going to create a dictionary, and this is just a blank dictionary, has nothing in it, and then I'm going to slice to the third value. Now there is no third value, so we are going to get a key error. However, in some situations, maybe instead of throwing back an error saying this doesn't exist, we want it to automatically make something, and something the same for all of the keys that are passed in without values. That is where the default dict comes into play. So from collections, we have to import default dict first, just like we do with a lot of our packages. And then we have to actually create a type, an object that is a default dict type. And the most important parameter here is this, where we say int. So what we're saying is, in this special dictionary, if somebody calls a key that's not there, automatically use an integer as the value pair. For example, now in SumDict, it's also blank. So this new dictionary we have, SumDict, it is blank. And when we call the third value, we would get a key error if it was a regular dictionary, but in this situation, we get a 0. No matter what number we put in here, it's going to automatically put an integer. Now that's really cool, because then maybe we want to do some kind of a math, maybe you want to build some kind of a giant dictionary that has zeros for all the values that aren't filled in, but then numbers in other parts. Or we can even put in other types. So here we can try putting a string in, and when we run it, we are going to get a blank string in return. So now the dictionary actually has a key of 4 with a string value after it. And you'll see in our applications play video, there's some really cool ways to make hierarchical trees or APIs and some things, some kind of more complicated things, but it's nice to not get an error thrown back at you, but just have some kind of a default parameter that the dictionary knows that it should have if it gets incomplete information. So that's it. You are now up on dictionaries. Thanks for dicking around with me. Subscribe to the Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations. Scope's an important concept, so we're going to start by looking at some basic examples of what we mean, where variables can be, where they can't be. Then we're going to look at some more specific categories like locals and globals and the system globals, and then how we can make our own globals and what a global even means. Then we're going to talk about namespaces. I think of these as big long lists of variables we have access to. So we're going to talk about how you can actually find out what these are. How can you output the variables that you have in your namespace? And then also talk about the order that your code is actually written in. It's another important thing that decides what you have access to at what time. So at certain states, you don't have the same namespace as you do at other states. As you write code and move your way down a page, there's changes in the namespace along the way that you have to take account for. And then finally, we're going to talk about privacy. Now this relates to classes, so it's a little bit premature for what we're talking about, but I want to start implanting the idea that there's also what you could think of as a system of permissions. So let's talk scope. Scope's an important concept because it's really about what's in the area. I almost think of it in real life like something that would be geo-fenced in, or different rooms inside of a building, something like that. So for the example, I tried to make it kind of in the same way, and I want you to first imagine a kitchen. Now say you had one pie that was sitting on the counter, and we're going to call that pie Global Rhubarb. And then inside the fridge, there's another pie from the night before, and that's called Local Apple. Now you can really think of the two pies in a real world sense as being separated by the fridge. Let's say that one area is the kitchen counter and one area is inside of the refrigerator, and they are separated by that fridge door. Someone would need to open the door and actually put one of the pies in or take one of the pies out if you wanted to get past that boundary. So the concept of scope is like asking what pies are here on the counter right now and then what pies are in the fridge. But we can think of those as separate namespaces. We have a variable called pie, and we also have a variable called pie. So if these were written right next to each other, we know that one would override the other when the next line came. We know first this variable would be assigned this string, and then later it would be overwritten and then assigned this string next. But because it's inside of this refrigerator function, it's protected. Until it's called, that's not going to do anything. So just take a second to think about what's going on here. Pie is defined, and pie is about to be redefined in here. So if this function changes it, then pie is going to be apple underneath. But if it doesn't change it, it's going to be Global Rhubarb underneath. Okay, so let's run this in a second, but let's talk global and local scope. So the way I talked before about the fridge being its own area, that would be a local scope of the fridge, and the counter would be the local scope of the counter. But when you say something's a global, what you're saying is it can be everywhere. Whether I'm in the fridge or on the counter, I have access to some super pie, like some a lemon meringue pie, let's make it, that's floating near the ceiling and is just everywhere. It just follows me around. So when I'm in the kitchen, it's there, and this like floating, kind of like, I think of it kind of like a drone, like a floating lemon meringue pie that's on a drone that flies around with me. And whether I'm at the fridge or I'm at the counter, that lemon meringue pie is always within scooping distance of my spoon. So let's look at an example of what I mean. And now when we print out bake, what do you think is going to happen? Because this is returning the local scope of pie. Okay, we get local apple. Seems reasonable. It defined this thing inside, even though pie was defined before, it overrode it, and then it returned it into our bake variable here. And then when I go to look at pie, do you think that's been overridden? Because it was overwritten inside when we executed this function. Nope, global rhubarb. So it stayed on the outside. It's almost like it was like this lemon meringue pie was floating out here, but then when I was looking inside of the fridge, I like pulled it in and then replaced it with an apple pie and then ate the apple pie, but it was a clone. Like the other one's still floating up there, still remembering it's a meringue pie and it's gonna follow me to the next place. Man, Sometimes I blow my own mind with how good I am at metaphors. Now let's look at system globals. Maybe another way to think about this would be reserved keywords, but these are the ultra global namespaces. These are like just by entering the house, whether you're in the kitchen or you have your drone meringue pie next to you or any of that stuff, you can't change it. So TRUE, I can never make this a variable. I can never change it in any way. I will just get errors when I try to do something like that. So whenever we take a system global like true and we put it into a variable, we do make a copy of it, but we can never actually change true. It could never go the other way. But regular globals are usually defined with capitals. Now, it's important to remember that when we write a variable in all caps, what we're signaling to other programmers is that this is a global that you should set the parameter on, or that we really don't want you to mess with. It doesn't mean that they can't, it doesn't make it immutable, it's just still a regular variable, but there usually is something specific that the programmer's trying to bring your eye to, trying to bring attention to. We've assigned it the variable pink, this car color, and now we're going to try to change it with the function. So we have a new car color, which is the exact same variable. What color is inside? Blue and pink. Just like we did before, it's exactly what we expected. This new color took its cue from the inside of the function. But now let's look at it again, and this time let's use this keyword global. So now imagine that we take the exact same code where we're assigning a car color pink on the outside of the function, and then inside we're making a car color blue, and then we're returning that car color, but we're adding the global keyword to car color first. What we're saying is, hey, this thing is now global. Now, global meaning break the heck out of this fridge. I know you were an apple pie that was inside the refrigerator, but now I've strapped you to a drone so you can follow me around and you can get out of here too. So, what do you think is going to happen when we try to change this one? Well, first off, we get this syntax warning. Now, I was playing with this before recording, and I'm going to leave this syntax warning here. I do think this is not really how you would write a normal function that you were using global in, but for our example, when I'm trying to show the overriding, I'm going to leave it that way. So what's going to happen when we run this? Okay, blue, that makes sense. It took its cue from the inside. Car color overrode it. Then we made it a global, and then we returned it. But here's the powerful part. Because car color here was defined as a global, even though it was returned inside of this variable, it also was able to break out and override pink up here, which was defined inside here, which should be confined to the inside of this refrigerator. Rhubarb is now apple, people. The world is upside down. Global gave it so much power that it broke out of the refrigerator by itself and put itself on the counter and replaced the pie on the counter. So now we have an apple pie inside and outside. Pretty wild. So you can see why this global keyword can be a powerful thing. It can allow us to define something in a local space that can break out of that local space. So now let's talk about namespaces. Now, the way we were talking before about the pie being on the counter or in the fridge, that was something where you would look around and just see which pies are there. But when we're talking about programming, we don't have a physical world, a counter that we can look at. So namespaces are the equivalent. So imagine we're in the living room watching the football game, and we ask our, wife or husband or girlfriend or whatever, honey, I am curious what pies are in the refrigerator and what pies are on the counter right now. So she comes back with a list. She says, okay, on this post-it note, I've listed all of the pies that are on the counter. And then on this post-it note, I've listed all of the pies that are in the refrigerator. And then you look over and you're like, okay, on the counter, there's apple and pineapple and cheesecake. And then in the fridge, there's, apple and others. So the namespaces are those post-it notes with all of the lists on it. Because we don't actually have that physical space, we can look at that. So how do we output one of these lists? So first off, I just want to import this module pprint. It stands for pretty print, and it has nothing to do with namespaces or scopes. But when you print out a dictionary, it does a nice job of indenting them when you print out to console. So it's just an aesthetic thing, and this function would work just fine without. Just to prove it to you, I'll show, but it's a little bit ugly for an output. So when we wrap it in this nice function pprint, then we get it in a more indented way with this nice scroller. So that's the only reason we have that there. So don't get confused on that. Anyways, but here in our local, you can see that we have the variable car color and its value right now. We can think of these as key values, or we can think of these as variables in their current state. This is the container, and inside of it is the color blue, which is weird. Or inside of this cucumber, there is the value of truth. You know, that's the thing, and that's the thing about the core of a cucumber is that they are true. They are true blues. Actually, cucumbers are true blue inside. These are the variables we have access to. So now remember, inside of our fridge, our local space is defined much more narrowly. Out here, when we're just running it, it's saying, all right, my local space is pretty much my global space. I'm not inside any containers. If we're both if we're both in a house that has no refrigerators and all the pies are out in the main area, then the global and local space will be the same. But you can see once I put the local function inside of my own function, pie is being assigned to the string pecan. Then you see when I run this fridge function, there's only one thing that comes up, just this pie. In fact, if I get rid of that, there's nothing. Just an empty dictionary that has no variables. It's a refrigerator with no pies inside of it, which is a really sad thing. But no matter where we are, inside or outside, if we use globals, we get every variable that's available to us anywhere. So here's global ran by itself. And now you can see even if we call our global function from inside of our refrigerator, we will get everything. I guess a good way to put that is like the apple pie that's in the refrigerator is not something the guests know about until they open the fridge. So basically inside of the fridge we have access to the globals, but the globals don't go the other way and have access back. And that Python has built in these global and local functions that you can use. Code, there are some amazing magics we can use. For example, %who is going to show you all of your global variables. So you can see that a warm pie showed up and our pie from before, and even pprint. It is in the namespace because it's in its own object, its own name. And then cucumber from before and car color. So you can see this is the way in reality to do it, is just open up a new cell and put %. Now that we know about these powerful magics for clearing out our namespaces, I want to show you in a real world application why you would want to think about using these and how going down the page in a linear order from top to bottom and left to right is actually something that does come up. You need to really think about what's happened before and after certain points to reset. So yes, we'd like to reset everything. So looking at it, we know that our namespace is empty. There is no variables that have been defined, no names that have been defined. So if I want to find out what the cosine of 90 is, and I haven't brought in the math package or module, you can see that nothing is going to run. Makes sense, right? We haven't defined what math is. So that makes sense because the namespace is empty. But after we do import it, so now I've imported it, let's look at our namespace. So we have brought in math, and the only thing that we're seeing in our namespace is math. So now that I have access to math, I know that I can do math.cosine, and we can assign it to our variable, which should be a second name. And now you'll see that we have both. And also, whenever we see something here in namespace, it's also a trigger that we can probably find some methods. So if we do math dot and then tab, remember in Jupyter, it shows us all of the things we can do with it. Or if we went over here to even our variable that we made and did the same thing, you can actually see why the point would be. Like you try to run something, you don't see it, you check the namespace. Using this %who in Jupyter, it shows you what you have access to, what names you have access to, and then that kind of starts getting you thinking about how these tools can work together. It's like, think of if you're like a mechanic and you're like working on a car and you like scan around to see like what's close to me, screwdriver, a wrench, maybe I can use one of these tools. So it's just about scanning the area for what's available. Finally, let's talk privacy. Now, if you are going through this course in the passes, like we talked about earlier, you probably have seen classes, but if you're just sort of following these in a linear order, you probably haven't. Classes are going to be an important thing that we learn later, but for now you can think of them as souped up functions, and it's really the only place you're going to find variables that have different permissions like privacy on them. But let's go ahead and just get our head around them because we are talking about scope right now. And the scope of a variable or name is going to be where it's located, like on the counter or in the fridge. What we're now saying is that, like, if you look inside the fridge and you see an apple pie, you're like, sweet, I have access to it. It's in my namespace. But then you go to pick it up and there's a little note on it that says, like, this is Beth's pie, don't eat it or you're dead. And you're like, dang. So even though I can see it and I have access to the pie, I'm in my, office refrigerator or whatever, and it's actually somebody else's and I can't eat it or they're going to be mad at me. So that's what this is about. This is about taking a name and saying, hey, don't mess with it because it's got some other use. So if you see a name that has a single underscore like this one, underscore Sherlock Holmes, then you know that it's probably supposed to stay private. And just like in the office, you could eat somebody else's pie that they left in the fridge, you really shouldn't. And that's exactly how an underscore should be thought of, is that somebody made it, another programmer wrote it and said, hey, don't touch this. This is private. It's mine. I don't want it messed with for whatever reason, although you could. It's not really locked off or anything. It's just, it's sort of like suggested. Like, hey, like we're all in an office here. I'm writing code, you're writing code, don't mess with it because I put an underscore there. I want it to stay private. And then double underscore private is a little bit different. So this is, especially when we're dealing with a class, something you're going to see that is important. When there is a double underscore, or a dunder as it's sometimes called, then you're referring to something called name mangling, and you really can't mess with this pie. Like, this is the kind of pie that if you eat it, the fridge might not even work anymore, and you're going to break the whole refrigerator. Don't, if you see a double underscore, change it, because what's happening is Python is actually looking for these double underscores, and then it's changing it in classes so it has the class name in front of it. It's almost like an important utility function that when you're using classes, which are like blueprints for objects, when it's making the objects, it's going to need to see that that's a private variable or a private function so that it can overwrite it. So it might not make tons of sense if you haven't learned about classes yet, but the important thing is just to remember that anytime you see this double underscore, think to yourself, ooh, that should probably be behind the scenes or hidden, or I shouldn't be messing with it. That's like going to Disneyland and looking like over the gate. Like, that's not for the guests, you know? That's the double underscore. And this one's like, hey, don't mess with me. Like, I got my headphones in, you know, I know you could, like, if you need to, like, make eye contact and I'll take my earphones out, but really just, I'm trying to work right now. All right, so you learned a ton today. We're getting pretty advanced here. You guys are really starting to learn a lot about programming, so I will see you in the next lesson. Subscribe to the Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations. Are you ready to get funky with functions? Well, I hope so, because today we are going to be talking about functions. In a nutshell, we're going to learn the basics, the syntax of how they look, the keywords that we use, what they can do. Then we're going to talk about a very important concept related to functions, which is calling the function. How do you tell it to execute that code? How do you pass in variables? How do you get things back out of it? That's going to all be covered in the calling section. And then our final topic is going to be parameters, because there are stipulations that you can specify and some that are specified by Python as itself for what can go into a function and what can come out and how that looks. So we're going to learn about some of the styling that you can use when you're telling somebody else how to put a function in. We're going to talk about something called star args, which allows us to do lists. And then we're going to use something called star kwargs. So get ready to find out what all these funky words are about in this lesson. Functions. Funky functions, I mean. Let's go to Funky Town. Man, I wish I could afford that song. You know, the rights to use it. You even know what song that is because of how bad I sing. Who knows? But listen, today we are here to learn about functions. So why do you think that a gas pump is what I chose for our mnemonic? You put X amount of dollars in, and you can mathematically calculate what amount of gallons you're going to get out. So I like to think of functions as ratios, even though obviously they can have all sorts of logic. They don't have anything to do with ratios at the end of the day. But just to keep it in your head to start with, think, all right, every $1 that I put into this gas pump, I am going to get 1/2 of a gallon out. So if I put in $2, I get 1 gallon of gas. And we want to model that using a function. We would do a syntax that started with DEF for define or defining a function, short. And then we would give it a name using our normal naming conventions. We don't do camel case. We could, but we just conventionally don't. And we can't use dashes or the number 1 or a number here at the beginning. So we have gas pump. This looks good. And then we have an open and closed parentheses colon. Okay, this is just a syntax to get used to. And in here is where we're passing our variable. Now this dollars can be anything. It's whatever variable we choose to make it. It can be that Captain Picard UTF-8 icon I used before. It can be anything that Python understands as long as we use it as a symbol to remember what we're using it for inside. So name this something that makes sense to what you're doing in here. Think of everything in here as something that's enclosed kind of in Tupperware. Different than our variable because that just holds a state. but an entire working machine, like a toaster. Think of a toaster with all of its little components, and they're all in here. Those components only interact inside the shell of the toaster. And here we take whatever's passed in. It could be $5, it could be $50, depends on how much gas you need for your car. And then it's going to multiply it by a half, by 0.5, and it's going to create a new variable, gallons. Now this gallons variable is stuck inside of the function. There's no way to get it out unless we explicitly ask for it using this keyword, return. So we'll talk about that in a second, but let's just look at an example here. This is my function for a gas pump. It's going to give you half a gallon for each dollar you put in. So we're going to define how much cash we have. We have $14 in cash. And then we're going to pass it in. Okay, this number 14, it could go right here also. We don't necessarily need it to be a variable, but just to show that you can, it will go in to here, it will process, and it will return whatever this gallons total is. Are you ready to pump some gas? Done. Right? $14. We got 7 gallons of gas. And now our, fast motorcycle, rebel without a cause, Harley Davidson is all, full of gas and pumped up, ready to cruise the open road. So, if we're going to be cruising the open road, we're probably going to need to make some calls. So why don't we talk about calling a function? Very punny, Dylan. Very punny. Ring, ring, ring. Hey, it's your conscious here. Would you like a bowl full of melted contacts? Like contacts, like the kind that you would put in your eye, like a whole bowl full of them melted down? No? That sounds disgusting, gross, and memorable, doesn't it? That it does. Let's talk about calling a function. So we've defined this function here, cup of melted contacts. It's hard to say because it's not a real thing that anyone would ever do. And cream. Okay, so we're passing in to this function. I imagine like a cup of coffee, but we're passing in melted contacts instead of coffee, and then some cream, probably to make it taste better. Blech. And we're going to return, instead of making the variable first and then returning the variable, we're just doing it all kind of in this shorthand notation. So we're just returning the sum of the two. So we have a function. Now what do you think is going to happen when we run this? Nothing. Kinda, but kinda not. Actually, there is a function that was just defined, but functions are containers. They're like toasters. They're there and they're ready to go, but until you stick that toast in them, they're not going to do anything. It looks like you plug in a toaster and it looks like it doesn't work, right? Because you haven't put toast in and pressed the button down. That's the same way. So calling is essentially the same thing as putting toast in the toaster and pressing the button. So let's make a couple variables here. So we're going to melt down 64 contacts. I hope you know what I mean, like contacts that people put in their eyes for good vision. I imagine like a bunch of them, 64 or 100 or whatever, and then you put them in a bowl, you put them in the microwave, and you just melt them into a liquid, okay? Because they're probably plastic or something weird like that. Okay, so that's what we have for our variables. Now, what do you think is going to happen when our function doesn't have any logic in it, except it just has this keyword pass? So we are passing in this number, 64, and we're also passing in this number 4. What's going to happen? Nothing. Oops. So that's kind of weird. Now that's a totally pointless function, but you might see something like this in code because you know you're going to need it later, or kind of like a reminder that you're going to do something. But in essence, this function that we've created called morning drink really has no use. So let's go ahead and start filling it in with some stuff that might actually do something. So what do you think is going to happen if we don't have a return, but we do have some logic inside? Well, following what we said before, it will process that. These two have been added together, but they didn't go anywhere. They didn't get returned. They didn't get put into a variable. So, Python's just got this like toaster that's like, hey, I'm ready to be pressed. Now I have the mechanics inside of the toaster, and you can press the button and put toast in me, but you just haven't yet. Now this is like a toaster that has nothing inside of it. This is like a toaster that just needs some toast. So let's give it everything that it needs. Let's think of this return keyword as pressing that button and putting toast in our toaster. 68. All right, so what happened here? Let's just remind ourselves 64 and 4 are the two variables that we passed in. That makes sense. So 64 came in here, 4 came in here. What was pairs is now melted contacts, okay? So that's important to keep. This is a variable of the number 64. And it just becomes this, okay? These don't have to match up, even though it seems kind of like they kind of should. Like you could go the extra mile and like make it so that this is also melted contacts, and you define melted contacts as the variable, and that could be smart for your situation, but just important to know that this is totally separate. Okay, now that we see that it's working, let's make a point to separate these two concepts. So we have what I consider the Tupperware part up here, the logic, the container, the toaster, and then I have the part where you put the bread in down here. So we don't have to put them right next to each other. So in this case, the toaster analogy really breaks down. Like this is like almost like a light switch, or if we could put the toast in the wall somewhere else, but the toaster was like on the other side of the room and then sent the heat over or something weird. But anyways, the point is that these two are totally separate. So you should think of this as being something that can be somewhere else in your code, right? Like put it way down here and you can run it and you still get the same response, okay? It just kind of magically travels through the air, and this is what makes it powerful, is that we can write all of these complex functions, and the functions can have functions inside of them, and they can call on others, and there's a huge stack of logic and all this amazing stuff your computer can do, and you just write something like here, like, you know, make me a morning drink, or, you know, move my mouse to the right, and it does all the logic to move all the other things and all the pixels around, and, you know, kind of the mind-boggling stuff is done separately, and it's contained in its own world. Okay, well now we know that the function works, but you might ask yourself, how would I know if I didn't write the function myself, if you didn't have first-hand knowledge? Well, luckily Python helps us with that too, because there is a callable function that we can pass our function, or actually any other object, because everything's an object in Python, into to find out if it's callable or not. So here's an example, the tiniest, simplest function I can imagine. Actually, we can make it more. Let's call it a. The function a. We define it, we name it, we give it the parameters with no we have parentheses for the parameters with no variables passed in, the colon to give it the statement that it's over, and then pass. Now, it's kind of unique to have it up there. Usually you would see it down one block, but it actually works if it's just passed in this kind of shorthand notation. So, we have a. Can we run this? True or false? True, because it's a valid function, right? There it is, right in front of us. So we also can check other things. So we know we define morning drink. This should be callable too. Yep. And what about the number 1, an integer? Well, an integer is not really callable in my head. It's not a function. Doesn't do anything. You can't pass anything into it. But who knows? Python's weird. Oh, we were correct. False. You cannot pass it in. And you might think a variable, all right, well, that's a container. It's got some stuff inside of it. Maybe that's callable. So let's find out if our 2 knees can be called. False. So it's easy to find out what's callable and what's not. But what's the syntax to actually make a call? Ring, ring, ring. Yellow. Would you accept a collect call from simple function, no parameters being passed in? It's a 3 times 4 return. Yes, yes, I will. You even know what you probably don't even know what I'm saying there. Collect calls. It's an watch old movies, people. It's how old people used to make calls, I guess, or old poor people made calls. So here's the problem with the syntax. If you don't make the call with the parentheses on it, meaning that there could be parameters, even though in this case there's not, but you have to say I could be passing in some parameters. If you forget to do it, which is a really common mistake, you don't even really get an error. So you have to be kind of aware of it, because it is just what it says it is. It's a function. It's kind of like a variable, even though you never put it in a container. It's in this private place, dunder main, and it's dot simple. And then it sort of attached it to this behind the scenes method. Okay, so if you see this, just realize, oh, I forgot the parentheses. That's the only thing you need. Much better. Then you can call this, and it's actually going to process what's inside and do the return. So this is kind of like working with the Tupperware. This is like moving it around or looking at it. It's defined up here in sort of the same way a variable would be, but this is actually execute. This is do something, like go ahead and process that and give me your return. And this is also where we will be passing in things when we get to our parameter section. So quick touching on annotations. Annotations are not required. In other programming languages, you have to specify things like this, but you don't in Python. So if you want to specify, for the sake of clarity, that you want to pass in a parameter, and you want that parameter to be an integer, so don't pass me a string. You can actually use colon, kind of like a dictionary here, and you can say, all right, this is the variable. Remember, x is anything you want to name it, as long as you want to work with it in here. But you can say, I want it to be of type integer, or of type string, or of type float. And you can use this arrow here with a list to say you will be getting back a list. Check this out. Shopping equals add. Okay, this is a function. You can see it defined right there. And it's got the number 4. This is an integer. It's got a string, which is going to correspond to a string. And it's got 4.4, which means it's a float. So it's going to give us a list in return because we specified. So look down here. When we do shift tab, it gives us some information here saying pass me in an integer, pass me in a string, pass me in a float. So that's really the power of it. When you're working with a team, they can see what you were expecting, or it gives them more clarity on what you need. And it's not going to throw an error if you give it the wrong thing. It's just going to work also, or work or not work, depending on what the logic is. But it's not necessarily something that is enforced either. So keep that in mind. And you can see that the type we got back was a list, just like I said it would. Okay, anyways, that's annotations. Okay, enough about the topic of calling. Time to hang up on that topic, you know what I mean. Very punny, Dylan. Let's talk parameters. Very cool stuff. These are the things that we're passing into our functions to be processed. These are the dollars in the gas station example. So there's a few styles on how you can put them. Let's start with the most basic. We have a couple variables, bm here and ym, and they're just defined as these two numbers. And we have a function called Hungry Hippo. It's going to take in an x argument and a y argument. Remember, we named these and matched them here, and it's going to subtract y from x. Okay, so you know, what is it? Subtraction is not commutative. It's whatever the opposite of commutative is, so it has to be done in a specific way. So watch what happens. When we have a function and we call it with bm first, it's going to take 7 in the first argument, which is going to become x, which is going to make it 7. And then we are going to subtract y, which is going to be the ym argument, which is going to come in here and subtract there. So we're going to start with 7, and we're going to subtract y. Now, it will still work if we reverse it. But because the logic needs it in a certain order, we are going to get a different answer. We're going to get -4. So this is something to be careful of. Well, I mean, we can't just be passing in parameters like willy-nilly on this thing, you know? It's not going to know which order you want things in. So we have a few options. One, you can make sure that the order goes in correctly, always starting with the first argument, second argument. Or we can actually specify. So in cases like this where we need things to be in the correct order, we can be explicit about the variables we're passing in. So in this example, you'll see that we set y and x the same way we did up here. But in this case, we're saying y is equal to ym. And we make sure that the variable 3 that we have is in the variable named ym. When you do this, it will go the same no matter what order they're in. So watch this. For example, we're going to get out 4 here. And we also could rearrange this and still get out 4. So it's going to be invariant to the order that they're in, for lack of a better word. Now let's look at a new function where we have this equal sign on the opposite part. Instead of having it down here where we're calling, we're actually having it up here where the function is. So this is interesting. Do you think it does the same thing? Let's try. 5. All right, so I think you kind of get it just now that this is acting as a default argument. If we were to put in something else over the x, like 10, it will overwrite it. But if no arguments are passed in, it's going to default to 5. So this is a really powerful thing to do if you would get an error if no argument was passed in. But you know, sometimes they're going to be lazy, the user is going to be lazy or whatever, and you just want to make sure that something goes in, and a 5 is a good default value. So x equals up here in the function is an automatic default position. So we can mix and match the two. I just kind of want to show you how you can have something that's required to be passed in, or you can have something that's required / it has a default, so it's kind of optional in a sense, but it does need an argument. It's not optional to have an argument, but it's optional to pass it a new one because it's got a default state. So here's an example of that. We can pass it ym, get 3. Yeah, we're going to have a missing missing error here, so the positional argument x is gone. This is referring to how we have passed in one argument, which is all that's really required from the mix and match, but it's not the right one because we were so explicit about saying that ym is only going to replace this one that has the default. It's not going to work. But we could say it's x, and then we would have something that ran. So what do you think about a triple threat? Nobody likes a triple threat. Double threats are terrible. Single threats are terrible. Triple threats are, oh, they're a home run. Okay, got a function. First, second, and third are going to be the variables we pass in, and we're going to add them together to see where our runner goes. So we place the arguments in the function call with a comma between the two to separate them out. That makes it so that it's first, comma, first, the number 1, then comma. So it's going to take all these together and add them up, and of course we get 6. You already knew that. And that's it for style part of parameters. Now we're going to talk about args and kwargs, the coolest words in Python. So what does passing in star args do? I will show you. It means that we can pass in something of varying length, whether it has 2 items or 4 items or 50 items, as many items as your memory can handle. By putting star args up here, it's going to take in the entire list of everything that you pass in. Another really powerful thing, if you have a function that just says, you know, process however much comes in. I don't need to know how many times a variable is going to come in. Just every time I see one, this is what I'm going to do. So do you think we can make some specific and some of the star arg style in the same function? Can we have some that are just like, I need these, and then the rest are like, and anything else you got, but I gotta have these? Oh yeah, of course. That was really a setup question, let's be honest. But here you can see we have first required, second required, third required, and then as many more as we want to pass in. So when we make the call, we have this star args up here. We have the first one, 1 tequila, it's got to go in. Second, 2 tequila goes in. Third tequila, and then floor plus the rest, car and jail. Hey, it's your decision. Let's talk star kwargs. Star kwargs, I just like saying it. Star kwargs. What do you think adding star kwargs will do to this function? Did you guess that? Cabbage equals vegetable? Well, what's happening here is we're able to not just pass in a long list. We're actually able to pass in pairs. So this creates a dictionary on the back end that we don't really see, and it's combining the two things as they come in and keeping them grouped together. So when something gets passed in as star kwargs, we can run this for loop. And remember before we talked about having an index and a value, a key and a value using this .items method. Well, we can use that to actually see what's going on. We can pull a name and a value out of what's passed in through star kwargs. And we can put them in these positions, right? The first position is going to be the name, and then the second position is going to be the value from the string video. Remember, this equal sign is only a string of text. This could be like, hi guys, or whatever. That's not an actual equal sign. That's just part of what I'm showing you because these two are connected together. And when they come in as apple equals a fruit. Okay, so it's a string, like a tag that we're putting on top of it. And then we're passing in a real variable called cabbage, and we're saying, by the way, that's a vegetable. So we can throw in these little tags with it, which can help us when we get more complex logic inside of a function. Okay, so let's just break this down from the top, because I'm not going to pretend it's really easy at the point we're at now, but it can be worked through. So we have a new function. We're defining it. Name bar makes sense. It's getting a first, second, and third argument. These are just single arguments. And then we're giving it this star kwargs, the special options. That's going to be this kind of key value dictionary styled pair. Then we're closing out the definition and we're saying, here's the logic. Then we're going to make an if statement. So we're going back to our conditionals and we're saying, bring in this dictionary of stuff and get out the item action if it was passed in, which it was passed in down here. And we're saying, once you see what that is, if it's this and it's equal to this, then execute this logic, adding this together and printing it out, okay? So it's a little tricky, but when we call the function, we're passing in the first 3 parameters that are just singles. Then we have this pair here. Action comes with sum, and then number comes with first. So we get the sum is 6. Kind of makes sense. Keep thinking about it. Look it over. You can always download the notebook from my GitHub. And then I just want to show you kind of a fun ending. Let's talk about unpacking. It's just a really cool thing that you can save a ton of time doing when you really get your head around. Not totally necessary as a beginner, but just want to show it to you. We can make this function called alphabet, and we can bring in A, B, and C. Get the first 3 letters of the alphabet, and we do nothing but print them. So we can pass in a dictionary. We can pass in a dictionary with 2 stars, or we can pass in a list with star. So star arg, and star kwarg. Here is what happens. ABC, 1, 2, 3, and 10, 20, 30. So the first one, it's the dictionary. It has just a single star in front of it, which is just an arg, not a kwarg. But I also said that only the kwargs were the dictionaries, right? So when it sees the dictionary come in, it just says, all right, there's only 1 star here, so it's an argument. Just use that argument, and that argument, and it just throws away the value that's paired up with the key, and just uses the keys by itself. But when you pass in the star kwarg, the dictionary then brings you the exact opposite. It only uses this as a label and brings you the value, and the value. And then if you bring in a list, you just want to use a single, which makes sense because there's only 1 space. There's no colon and another key value pair. It's just a key or an item from a list. So kind of get your head around that, and you will understand how to pass things into functions, how useful it can be to store all that code, and on the broader context, just how amazing functions are. A ton of layers of functions below what we have to deal with, and it's really amazing. It's what makes computers and all this magical tech stuff work. So that's it. We'll see you next time. Subscribe to our Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations. All right, get ready for this how-to video where we discuss nesting. We're going to talk about passing functions left and right. We're going to talk about a really important concept called closure, meaning like what variables are packaged along with it when we're sending functions off to go visit places and do different things. And that's what makes them first class, because they have the ability to do anything that a Python object does, which is pretty incredible when you start thinking about it. And then we're going to talk about nesting and the differences in the way we can nest the different functions and what it means for how we call and execute them. And of course, closing on closure, we're going to build on the concept from the Y videos where we talk about being at the post office and closing a box with a package inside of it and the entire environment of the post office going into the box also. So when your friend opens the box, he's also inside the post office. So we're going to go through and just show a bunch of experiments and examples to see where and when you can access what to hopefully drive that concept home. So get ready. Let's talk nesting. All right, let's start with first-class functions. Remember that airplane seat, that first-class experience? That's what we're about to go through now. So imagine yourself with all of that beautiful, hoity-toity stuff going on your flight. So here's what we're going to look at. We're going to look at functions and how they can be passed into one another. So we're going to define a function. It's just called rando. We import the random module, and it returns a random number between 1 and 10. So I'm going to run this cell multiple times, and you'll see that we get different answers each time we run it. So it's picking a random number. So we have this function rando. We know how to call it. We know it provides a random number. Here's the question. Can we use a function as a parameter? And if we do we add it with the parentheses or without the parentheses? What happens? So here we're defining a new function. This doesn't have to match up, remember, because we're inside of the parentheses here. So this just has to match whatever logic it is. It is a variable in itself. This is the variable's contents. This is the shot glass. This is the liquor. We have defined a robin's nest, and we want to bring in rando. But when we do, we're going to have some kind of return here, and then we're going to do some logic. We're going to add 100. So we know we're getting a number. We know they're both of the type integer, so that should work. We should get some kind of random number here and add 100 to it and then return it if we're allowed to pass functions in as parameters. And as you probably guessed, because in Python we have first-class functions, we can pass them right in. So let me just run this cell a few times and you'll see that we get that random portion, 1 through 10, is always added to the static 100, the constant that we get from the second function. So a cool way to think about, we have these little packages of code and they can actually be passed into packages of code. It's also easy now to start thinking about how Python really does so many powerful things. When you start writing programs that do amazing things on your phone and applications that tap into all these other resources, you can kind of imagine that you're just on the top of all of these nested functions. It's calling on a function that could be calling on a function, it's calling on a function, and they're all hidden from you, but they're going all the way down to the ones and zeros, the binary that actually runs computers or goes into huge databases and does more complicated queries just because you ask for something simple. So really cool to understand first-class functions means that functions are treated as objects and they have all of those same first-class rights. So we talked about passing a function into a function, but let's talk about nesting, meaning the functions are inside of the functions. So we can look at it a couple ways. First, we can think of them as separate containers where one is just going around like a kitchen and grabbing whatever it needs because it's got access to everything in the kitchen. And that's what I call this separate category. So the way to think about this in code is to define a function that does something simple, like just returns the string of text fly. We'll run that so you can see that it works. And then let's define another function. And what it's going to do is it's going to return bird, and then it's going to multiply it by 5. So it's kind of like our first-class function here, but you might be asking yourself, but you didn't pass anything in. That leads to an interesting question. What if we would have put rando just right in there like that? What if we, in fact, don't pass in anything? That and that. Does that work? Oh, it does. Look. We don't even need to pass it in. So it does work when you pass it in, and in some cases you want to because you can't just have everything floating around everywhere. But it's good to know that we can grab them just like we would any other variable. So here we can just say, take that function, multiply it by 5, and return fly, 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 fly. Okay, so when I mean separate, what I mean is floating out there in the environment, a variable that we have access to. It's an object, technically, but it's just an object that we have access to at any given time. Like we could call it at any given time. We can also build some new container and put it in the container because it's already in the kitchen. It's like out on the counter, and we can put it in the Tupperware. Stuff that's in the Tupperware can't necessarily get out of the Tupperware and get onto the kitchen counter. I must be hungry. I wonder why I'm making all these kitchen analogies. Okay, but let's look at it together. So this is another function that we're calling nest2, and inside of it is another function. So the function wasn't created outside, and then we're just calling it in. This thing solely exists. Its whole life is inside of this cage. It's inside of nest2. Bird2 doesn't know what it's like outside. But what's interesting is we can define it. It is in the scope inside of this function. So maybe the best way to think about this is to focus on the inner function first. Pretend this is all of our world. Don't worry about the indentation. All we're doing is returning this string egg. But who's going to call that? Well, we could call it down here if we were pretending this wasn't spaced out and this didn't exist. So maybe we can just add a return and then put a definition. So we're now indented one layer, and this is automatically going to get called and then returned. Okay? So that's interesting. Egg is solely living in here, and we can't call it outside. So right here, I can't call bird2, for example. There's nothing there. But with the separate one, I could call, well, I already have. It's pretty obvious, but yeah, I could call bird. Right? Because it's already there. So interesting just to think about how we nest things and where the scope of variables and access is. Let's talk about closure. So closure is one of my favorite topics, but kind of tricky to understand. So for those of you who are like just playing my video in the background while you know, like write political comments, now is the time to stop doing that and actually watch the video. Because if you don't see this, it's not going to click very easily. It's conceptually hard to understand, but seeing examples, I think, is the most concrete way to deal with it. So I'm excited for this. We're going to talk about Clojure with some experiments that I was testing before that will hopefully demonstrate this. So here's our scenario. We're a tiny little bird. We're like a little bird that can't fly yet, and we're inside of a nest, and we're inside of the jungle, okay? We're in a tree, like our mother bird has left, so we're just hanging by ourselves, and we don't want to jump out of the nest down to the ground because we don't know how to fly. We'll probably get eaten and we don't know how to get back to our place. But we can like hop a little bit. So we can like hop out of our little stick nest and we can go up and down the branches and we can pick little branches or eat little bugs, stuff like that that's on the branch. Okay? Trust me, this is going somewhere. Otherwise, you might end up a garbage man in the stinkiest part of town and assigned to only the stinky garbage. We have a variable here called stones3. It's outside of every function that we have. Obviously, we have access to it. It's at the top. Then we have our first function, which is our nest. So we're moving from the forest floor, where the stones are, up the tree into our nest. It's another little container. And we have inside of here some sticks. We don't have access to that variable from the outside, but if you're in this function, you do. Then we go inside of the bird. Inside of the bird has bones. So we have the variables stones, sticks, and bones, and they're at different levels of scope. So now we have this print function in the most inner nested function, and it's printing sticks, stones, and bones. So we're checking to make sure it has access to all three of these levels. We're just going to make that function. It's not executed yet, but that's the layout. Okay, so now let's just double check what we have access to. Stones3 we do have access to because it's on the outermost thing. Sticks3 we don't because it's nested inside of a function and we can't get to that. We haven't executed that. And then, of course, this function we can't even call. We can't even execute birds3 because it's inside of another function which we don't have permissions for. So that one's protected too. So now we know what we do and don't have access to. So if we take nest3, our outermost function, and we run it, it is going to return bird3, which is a call to the inner function, and it's using the parentheses, so you know it's going to execute the logic that's inside of here. So it should print all of these out. And what do we get? Yes, by just calling this outer function, which then in turn calls the inner function, which then in turn says, do I have access to this, this, and this, which it does, and does. Okay? All right, so execution with parentheses down here. Now, let's look at it without parentheses. So this is basically the exact same, except now I've changed everything from 3 to 4, just so we know that we're working with fresh variables, nothing's coming down the page. And one big change here is that the returned variable isn't being executed. That's different from this one, because we had the parentheses around it. So this one's just passing it in, and it is going to use Clojure to bring all of these variables into it, and then we can pass it around later. So same thing, stones, sticks, bones, execute from the inside. When we define this function and then run nest4, we'll get something different. Instead of executing it, we just get some information saying, hey, this is a variable. It could be ran, but right now you're getting back just bird4, the variable, holding the entire function and all of the namespace and all of these variables at all three layers. So we can put this variable, which is unexecuted, into a new variable, and then we can pass it around. So now we can run this, and instead of using that function to execute that function, it's just going to pass all that information into a new variable called shotglass. Makes sense, shot glasses hold things. And if we look at this, we'll see the same thing as before, so we just passed it in, no problems there. But here's the question. When we take shot glass and we add the parentheses, is it the same as having the parentheses in here? Do you think it's going to actually execute this code? Surprise, surprise. It can. And it has access to sticks4, stones4, and bones4. So that means all of this stuff, that, and that, it all got packaged in here. So really, Bird 4 is amazing. Like, it was like, I'm going to get a stone, I'm going to get a stick, I'm going to get bones. You can pass me into another variable, and then you can execute that variable later, and it has all of that stuff in it. So when we're talking about closure, we're talking about this concept that the function itself has like brought in all of these variables that are normally just floating around. And I mean, it kind of makes sense that it has access to it here, but it's sort of surprising that it has access to it down here. So it's really bringing a lot in with it. The entire environment's in there. So now let's take it a step further and look at what happens when we actually repackage that variable that's holding a function that's also got a nested function, and it's got some logic that's looking at variables that are spread out all over the scopes. So here we are, stone 5. This is the same as last time. We just added 5 to everything. Now we're going to take this. Remember, the return is coming in without the execution, no parentheses there. And we're going to put it in a variable. This is the same as shot glasses last time, just a new name. We put it in closed package. And now I've defined a whole nother function. So remember, now we're kind of going back into another Tupperware container. So we are going to check to see if you can actually return it. So before I run this function, what I'm saying is I have a new function, and its goal is just to return whatever is in mystery. And what I'm going to put into it is the closed package, this equivalent to shot glass, and I'm going to put the parentheses on it. So it should execute this, that should execute that, which should check to see if all those variables are there. But remember, this is now all contained inside of this can I print world. Like, all of these variables that were all outside, they can't get out of this because it's enclosed in its own Tupperware. So now it's like before, where we'd open the box and we'd look around and we were like actually in the post office, like everything came out of the box, the entire environment. But now that entire post office is inside like another little Tupperware container. You know, like there's another wall on the outside that we definitely don't have access to. Those variables are not floating everywhere in our code, but they will be contained inside of here. So, can I print? You certainly can. Sticks 5, stones 5, and bones 5. So pretty interesting stuff. Just weird to take all these variables and like package them in with something and then put them in something else. And I mean, it's really just fascinating to see how Clojure works. I mean, it can let you get access to variables when you're pulling up modules, things like that. So just powerful, interesting, and something that you should know about. Now go back to doing your political comments. You Republican, Democrat, Independent, or other. Channel your inner Martha Stewart for this one. We're talking decorators. You've seen this set of functions before, but the last time you saw them, they were reversed, and we had rando on top. Adds 100 to the random number generated here. And that is possible because even though it's floating in the scope of this DEC function, it can be read by the inner function, and then the call gets returned, not executed in here because there's no parentheses. It gets passed into this rando dec variable, and then we execute it with the parentheses. Okay, if that didn't make sense, watch the last video. So let's doon. And what we get is exactly what we expected. Let me run it a few times. You can see that we keep getting our random integer added to the big number. So this is basically what a decorator is shorthand for. Decorators can be thought of a really simple way to take a general common function that you want to modify a lot of other functions. So it doesn't come up all the time, but I'm telling you that I never saw decorators like 7, 8 years ago, and now they're coming up all the time. So my most recent real-world example of dealing with a decorator is if you connect to Google's cloud infrastructure. They have decorators all over the place, and they're really powerful because you can make a function that does some kind of complicated computation, and then you'll add a decorator, which are these @ symbols, and then the name of a function that's been defined as a decorator. And what happens is Google takes your output and then sends it up into its cloud infrastructure and can then parallelize it or do processing or host an app in the cloud. It can do a whole bunch of functionality that you don't need to worry about anymore. You don't have to write all that stuff because it's general. Everybody wants the app to be fast, so you just add the decorator @fast to your function and Google figures out how to make it go fast. So with the world of APIs and this Internet of Things, I think you're going to see decorators popping up more and more. Now, what they do is sort of a shorthand. It could all be done with functions being passed into functions, but there's a lot of cases where it's just a waste of time to write all that stuff. So a decorator is something that you want to be general, something that you want to apply over and over again. Like if you had a house but you wanted every item and every wall and the house to be pink, you could write a decorator that says no matter what the thing is, after it's made and put in its place, color it pink, right? It's like bringing a can of spray paint in and just painting everything that you own pink. You would make that function of spray painting everything pink a decorator because it would apply to so many things. And it's really not that useful if you're just going to do it once. Like up here, it would be just as easy to make this two functions as it is to make one function that's a decorator and then apply it. Here is a situation where you might want to use a decorator. You might define, like at the top of your code, a topping. We're going to think about cakes in this example as our sort of mental visual mnemonic. So you imagine the topping of like frosting, and it can be put on any cake. It can be put on a chocolate, strawberry, or vanilla cake. We just pass in any cake. This is a variable that we've defined. And to make it a decorator function, we just need to do, well, nothing. We just call it later using @ symbol. So it's really easy to make decorators and even easier to use them. Here we pass in any cake, and the cakes in this case are going to be a number. For chocolate, 1 through 10. For strawberry, 11 through 20. It'll be a number here. And then we just do the same thing. We add 100 to it and then send it back for execution. So just like what you saw up here, we only now need to write one topping function because we know that we want frosting on all of our cakes. And then on each of our cakes, we just add @topping. So the way to think about it is whenever you see that @ symbol and then some kind of word, you automatically know, oh, that's some function somewhere else in my code. And once this logic executes, it's going to go traveling up here and go into there. So you can just take all of this and then pass it into topping, and then all of this and pass it into topping. And you can see when we run chocolate cake, which you think might just do what's here in the definition, like you think the code works down. In fact, that is one interesting thing, is that you can always think of code as moving down the page, except in this one situation. This is the only thing that's popping into my head right now, is times where you can add something above the execution line and it actually works. That's interesting. So here we call chocolate cake, and it does run all of this, but it takes that return, and instead of just giving it to you down here in the call like it should, it then puts it into the topping function. It automatically goes up here and passes it into that. So you can see when we run chocolate cake, we get that random number 1 through 10, and then it's added to 100. And we can do that over and over again, and we'll see that we'll always get a number between 1 and 110. Now moving down with strawberry, our number that's random is going to be between 11 and 20. So we got the same thing, but these numbers are always going to be between 110 and 120. And then doing it one last time, you can see it works for vanilla cake too. So you can imagine if you had thousands of these functions and you really just needed to add this little topping, or you have like a handful of these toppings that you sort of memorize, like shortcut functions that modify it in some way, especially something like cleaning up text before it goes out, or like rounding digits up so that they're whole numbers because you're presenting them to the user or in some kind of a graph. Like, it's great to just have a little function that does that, and then you can just apply it to everything that comes out. So there you go. Hope you're feeling very much like Martha Stewart now, and you're still imagining that weird pink house. Subscribe to our Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations. Welcome to this how-to video on comprehensions. Now, the reason I broke this out from the other videos is because we're really not learning any new core functionality. We've already learned how loops work, some of the amazing things they can do, and comprehensions are just going to be a way for us to shrink this code. It's going to be notation, it's going to be shorthand, and we can do all sorts of cool things in a much more simple way. So we're going to start by looking at types. How do we handle the different group types like lists, dictionaries, and sets? Then we're going to talk about operations. How do we use comprehensions and still bring operations that we might need in? Then the same with conditionals. How can comprehensions and conditionals work together? We're going to talk about nesting. You know, we can have loops inside of loops, so can we have comprehensions inside of comprehensions? We sure can, and we'll talk about why. And then we will talk about using range. And finally, a generator can also use comprehension. So we can use our yield statement and have that same overtime functionality with the pause that we talked about. And finally, we're going to look at a fun FizzBuzz problem, a problem that you'll very likely get on your very first programming interview, and how we can do that in comprehensions to make you look super sharp when you solve that problem. All right, let's do it. So we're going to go over lists, dictionaries, and sets to start with. So first off, let's look at an original way we might go through a loop over a list. So we've got this list defined. It's just got some strings in it. We call it old, so it's full of prunes and wrinkles and wheelchairs and such. And then what we could do before was write a for loop. We could say for I in old. And we know what we're doing here is saying old must be something that we can iterate over, and this I stands for the individual elements, the pockets, if you will. And we're going to take each one of those and perform this method of append onto a blank list, so we end up with a new loop list. Okay? Simple enough. So how would we do that with a comprehension that only takes one line instead of 1, 2, 3? Well, we could just say for I in old, just like we have up here, and the logic that we would normally have inside is just put right here. Now, logic in terms of operators would go here, like a multiplication, and we'll see that down here in a second. But we don't actually need to take a blank list and then append it, because this comprehension is inside of the brackets. And look, brackets are how we make lists. So these are important. You can't, this is not a willy-nilly kind of bracket situation. That's going to be important if you want it to be a list. Curly braces are going to make it a dictionary or a set. Let's look at that next. Boom. Prunes, wrinkles, and wheelchairs. Finn. Okay, dictionaries. Now this one's a little bit more tricky because we have keys and values. So I made a couple lists here. Now these are just classic lists. You can tell by the brackets of superhero identities in real life and as heroes. You know, Bruce Wayne and Batman, Clark Kent and Superman, etc. So the way we might loop over this dictionary in our previous how videos would have been to say for key and for value in, and then we would zip the two together and then go over them. So here we're making a blank dictionary, you can tell by the brackets that we used, and then we say take that dictionary and add R, which is our key, and make that equal to value. So make that key equal to that value that comes through from the zip. This new dictionary called Loop Dictionary, and it consists of these key value pairs, which was everything that was in these two separate lists. But can we do the same thing with comprehensions? Yes, we can. Dictionary comprehension looks pretty similar, right? For key value in zip, just like we had up here. Take what was inside nested and loop it up this way, except the fact that we're using a dictionary is defined by this outside. Comp dict. Done. Cool, huh? Okay, so lists and dictionaries. Now sets are close to lists, but one thing that's a little bit different about them, of course, is that you can't have duplicates. The old way of dealing with this would have been for n in nums. We would have just added it, kind of similar to append with the list. But the comprehension way, we can put the curly braces around it. And you're probably thinking, well, you just put curly braces around this comprehension, so how does it know it's not a dictionary comprehension? And that's just because Python's smart enough to know that we don't have keys and values. We just have, I guess, just a value here, or a key. A key and value are squished into one. It's a symbiotic relationship. But just because we're not saying, and like this was like k-v, then it would be expecting something that was a dictionary to come in, but since it's getting nums, which is a list, it's all confused. So we just make it a simple element that can be put into a set. So my set was created on the fly there. No need to do this part. Like, watch this. I think we can just do set 2. Boom, same thing, right? So don't let that trip you up. You don't actually need it to say my set there. We have our own set. And then just the very last thing is that when we do this with the square brackets, just remember that we're making not a set, but a list. So we are going to get all of our duplicates. So the difference between duplicates and not duplicates is curly braces for none and brackets for a sequential order that does have duplicates. All right, there's the basic types: lists, dicts, and sets. All right, now let's look at operations. And the good thing is you've really learned everything you need already. You know how loops worked, and then you just saw some examples of the basic comprehensions with basic group types. So now we're just going to add some layers to it. And this is just kind of a nuanced thing that you'll get familiar with over time on where to put operations and conditionals when you're doing comprehension. So it's good to just play with this one. This is a great notebook for you to just goof around with or test yourself and see if you can recreate some of these just to get familiar with them. I'll show you the first ones now. So we create a list of nums, and this time we're just saying no change. And we're not assigning it to a variable, so it's basically just going to print to console because we're inside a Jupyter Notebook, and it's going to stay a list because it's in the brackets around it, so it makes sense that it looks exactly like it did before. Then we're going to take a multiplication of each of them. So now we're saying for each element in this list, multiply it by 2. And you can see this would be the logic inside of the for loop. We just put it in front. So I like to think of it as something that would be like it would be underneath this, and it's now like moved up and to the left. So it's in front now. An easier way to read this as the old way would be like for I in nums, and then it would be do this multiplication. So same thing, we're going to get what we expect, the multiplication, everything has been multiplied by 2. And now I'm going to show you just one more kind of layer. So we're saying for this in nums, we have our answer here. Now normally we would do our logic. Because we want our logic to be behind an if statement, we put it at the end. If, then go ahead and print. If not, don't. This is going to be only our even number. I think we could just do multiply 2 again right there if you wanted to see that just for those few that it selected, or those 2 that it selected, you could actually do the operation on them. There you go. That's operations with list comprehensions. But remember, that could be dictionaries or sets or all sorts of different things. Next up, conditionals. Pretty much just as easy. The main thing to remember about conditionals and operations is operations usually are on the left. Like we only have one line now, so we take what would have been the top of our for loop or our while loop, and now we say operation stuff is mostly on the left. Conditional stuff is mostly on the right. If it's going to be an if statement or something's going to trigger on some kind of check, you're probably going to add that check to the right side of it. So let's just look at another example here. So we have a normal for loop where we're saying here's a list, and then go through all the items in the list, and if it's a modulo of 2 that brings no remainders, then we know it's an even number, so append it to my list. Easy enough, we just did that. And then we just have our normal for n in nums, which is just like for this item in my list or group type. Then we have our if statement, which would normally be down a line, but we're going to keep it in one line because we're doing comprehensions. And then you have the logic. So conditionals go on the right, operations go on the left. Well, I'm sure you're all wondering what this exciting banana example is about. Well, we're going to make a dictionary, and it's going to be assigned different fruits and vegetables and ducks and babies and their number of best friends, let's say. So we have the key value pair separated by the colon. Of course, the comma changes the elements, and the colon signifies the relationship between those two. Now, one thing we could do in a normal function is we could pass in both this dictionary list and then this custom value that's asking for a string. Okay, now this string is going to go into a function called starts with. Okay, this is a method that's just built into the string function. And one of the things we can do is put one of these dictionary comprehensions in the same line as the return. So look at how convenient that is. We've got this function that is pretty complicated. It's bringing in a dictionary. It's saying for these key value pairs, sort them by only the ones that start with the letter B. Even though we have apples and carrots, we don't want those. We just want bananas and baboons and babies. So we can put that all in one line, and that's cool. I mean, it's easy to read. We're saying for key value in this dictionary of items where this logic is applied, return both the key and the value. And don't get too caught up on functions. That's our next chapter, but we're basically passing these things in, and you can just see that comprehensions can be really powerful. We've now sorted what could be, a million item dictionary down to just the ones that start with the letter B, or maybe we just want baboon, so we just type that in and it searches that whole key value pair. So it's very interesting when you think about it. And down here we can take that, and it doesn't have to be inside of a function. We can just all of a sudden right here make it. We can just say it's a dictionary comprehension and here's what it needs to do. We could also give that a dictionary key value. So now we have give, which is our, just wanted you to see how easy that is. Be happy, baboons, babies, and bananas. That's our banana example. Now let's talk about nesting. Okay, so now let's talk about nesting comprehension. So first off, just you got to make sure that you know how to think about loops inside of loops, or else this isn't going to make sense in a normal way. So just to kind of recap, we have an outside loop that we've defined as letter, and it's got 4 pockets in it because it's a string with 4 characters. And then inside of that is another loop that has 4 pockets also. This time it's numbers inside of a list, but it's the same thing. So we can think of this as running just this outside loop once for A, and then what is inside the loop? Well, a whole nother loop that goes through 4 times. So we'll expect just for A to get 1, 2, 3, 4, and then just for B to get 1, 2, 3, 4. So you can see that's exactly what we get. We get 4 A's and then 4 B's and 4 C's. Okay, and then just to kind of get your head around it, if we add the print line up here, so that it's not inside of the second loop, we get it just once, because that's actually what's happening. We're doing it once, but we get these 4 times that it prints out. So just to run that, I want to make sure that you see that you'll get it once, A, and then 1, 2, 3, 4, and then B, 1, 2, 3, 4. Okay? So that lets us see what a comprehension with 2 loops looks like. Starting here, like our outside loop, 4 letters in A, B, C, D. That would be like right here. 4 letters in A, B, C, D. And then we have no colon, no way to signify to Python, just a space. And then we start 4 again, and it knows. And then 4 num in our numbers, which is the same as 4 num in our numbers. And then the thing that would be the print statement in the most inner part, the most nested part, is going to be on the front here. So it's not going to be printing from this level, it's going to be printing from this level. So we add that and we put it into this test list, and we get out 1, 2, 3, 4, just like we expected here. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. So the syntax, just remember, it's just 4 right after a 4, and then whatever you put here is going to be the innermost nested statement. Normally, if we wanted to work with a range, we might have a list like this one of a bag full of gold, silver, doubloons, I don't know, I'm not a pirate, and jewels. We can use this function length, and it's going to say 1, 2, 3, 4. I see 4 pockets. That's the length of it. And then range accepts an integer, and the number 4 will make a range, a list of 1, 2, 3, 4. So I'm printing before we assign here, and then we're printing again, so expect 2 print statements. But I did this one because I want you to see that this is actually a number, and then down here to see that it's actually the characters multiplied. So down here you'll see 0, 1, 2, 3, and that's because it found the length of 4, which we have the 0 indexing, and then it printed that out. And then it said for the index of that number, so for the first pocket, take that pocket and then multiply it by 5, and what's in that pocket is a string, so we end up with 5 pieces of gold and 5 pieces of silver and 5 doubloons, so we're getting rich, or doubloons, however you want to say it. Now, when we're doing, and I'm going to do this just to reset it, just back to 1. With list comprehensions, look, we can just say in bag. That would not work right here. If we take just bag and say, run that, we're going to get an error because it's got strings inside of it. But down here, it's smart enough to understand that we want to take that item and we want to multiply it by 5 and get 5 of our doubloons and gold. And it can handle the range by just sort of understanding that if you're in a comprehension, it's a range. Cool, huh? Here is our powerful yield keyword. So if we're going to use comprehensions for a list, we've seen this before. We take our element, we can do our operations to it. We say for x in blank, and then we have our group item here, our group type. So we run that, and you can see that we do have a list just as expected because we have brackets on the outside, the way that we make lists. But if we use parentheses, which normally would be a tuple if we weren't working with comprehensions, but we have the same logic, the for loop and the group item, we end up with a generator. Interesting. So that's the way to think about generators, with parentheses around the outside. And then of course we can convert them back and forth using our normal function, our iter function, or our list function. So there you go, just a little glance at how you would work with generators and comprehensions. And now finally, for my favorite thing, Fizz Buzz. It always reminds me of a soda. Like, is that something from The Simpsons? Fizz Cola or something? What does Bart Simpson drink? Not important, Dylan. Stay on topic. Can't believe I only had one Z in Fizz Buzz. That's such a lame error. Anyways, it's Fizz Buzz with two Z's. It's a little program, a little test that a lot of newbies get, and the goal is to write a program that prints numbers from 1 to 100, but for multiples of 3, it prints Fizz, for multiples of 5, it prints Buzz, and then for multiples of 15, it prints Fizz Buzz, and sometimes there's little variations of that. Using comprehensions, we can write it in one line, so you look very impressive if you do this at your first job interview. So, I think you should play with this on your own and make sure you understand how it all kind of fits together. And here is what we're doing. We're at the end, we're creating a range. In here you can see a handful of these statements where they start repeating. Modulo 3 is equal to 0, and then we say else, and then we kind of keep going down. So here it is in one line. Boom. Fizz Buzz. Print it. All in a big long list. 1, 2, Fizz, 4, Buzz, 5 Fizz, and then 7, 8, yada yada. This is the same line, we're just spacing it out so you can read it a little bit more, but this is a one-line solution, and it's the same as up here, but this way you can see it a little bit better. So we're saying to print this, and then we say if x is the modulo 15, and that is equal to 0, else, and then yada yada, and then else, yada yada, and then else. And then we do this for the range 1 through 100. You'll see this will print the same thing, but just a better way to look at it. Very cool, very fun. Fizz Buzz away with two Z's. And we are done with comprehensions. I think it's time to go visit our memory palace and get a little crazy before we move in to the all-powerful section of functions, 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 functions. Subscribe to our Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations. In today's lesson, we will be learning the how of programming by reviewing code examples that demonstrate the ways we can work with recursion, iteration, and generators. So recursion is defined as something that calls itself, and we're going to look at a couple examples that demonstrate a factorial and a Fibonacci sequence return. Then, using classic iteration and getting the same result as recursion, then compare the difference. And finally, we're going to talk about generators. Now, generators are an entirely different type of object in Python, and they're very powerful because they have the ability to generate their returns each sequential step, which allows us to pause or halt the system in many different places. And that can be a really powerful thing. We're going to look at the time it takes to execute generators. We're going to show a couple examples of generators in traditional looping iteration. So get ready, because this is going to be an exciting lesson that hopefully is explained clearly enough that you don't have to iterate over it too many times. Let's start talking about recursion. Let's start talking about recursion. Let's start talking about recursion in the sense of factorials. So here is what makes recursion recursion. It has a mini version of itself inside of its own logic. It is a tricky thing to get your head around, but the important way to look at it syntactically is when you see the name of a function up here repeated again somewhere inside of the logic. But another way to think about them is that they're sort of stacking on top of one another in sort of a pyramid shape. So when we look for factorial 5, we then need to wait for a whole new function, which is actually getting the input of 4 instead of 5 to find its answer, which is then waiting for a whole new function, which gets the input of 3, not 5 or 4, to get its answer. And then when it finally gets to the answer, when it finally gets a 1 input and it gets a return, then it solves this one, which solves this one, which solves this one, which solves this one back up the chain. So the way to look at this inside is usually with an if-else, we're saying finally if you get to the input of 1, we have an actual answer for you. But other than that, we're just explaining the logic that's going to get you to the answer no matter how far out you are from the number 1. And you can see that right here. We're taking the number n, which we're going to put in as 5, could be any number, and then we're multiplying it by this exact same function, but that function is taking in the number 5 minus 1, and so on, and then the next one, and the next one, and the next one. Let's just run this, and you can see that each time we printed, each time it made one of these, we had a different print statement here. So even though you see one print statement, we do get it printed out 5 times because each time was a whole different function. This whole function is inside of just this call to another whole function, which has a call to another whole function. So that is how you think of recursion and why it's different than traditional looping. So now let's show another example. Instead of the factorial example, I'm looking to create Fibonacci. If you don't remember the Fibonacci sequence, it's 1 plus 1 is 2, and then 1 plus 2 is 3, and then 2 plus 3 is 5. So one of the ways we can do this using recursion is by calling a function that is decremented by 1 and then adding it to another function that's decremented by 2. We're running this exact same process. We're saying to get this answer, first put in that one and that one. And then to get that answer, put in that one and that one. So you can see we can actually run this. Let me get this thing out of the way. You can see we can actually run this function multiple times, so each one of these is a separate call, but I wanted to show you that it does make the pattern. If we recall the first place, the second, the third, the fourth, the fifth, and so on in the list. So you can see that we can get it that way, but another example of being able to find the actual function with some kind of different argument inside of the exact same function with the original argument, and then something modifying it down there. Okay, so that is recursion in a nutshell. Nutshell, nutshell, nutshell. Now let's talk about iteration, because iteration is a more abstract notion in the same way recursion is. It's a conceptual thing that goes beyond just Python or a single programming language. And iteration is simply the process of doing something to every element in some kind of a sequence. I always think of it in my head first as a list of items, and you're doing something to all of them. Like if you have an actual notepad, like a physical to-do list, I consider that iteration when you cross out each item when they're done. You say, is this item done? You do the logic, and then you cross it out. But that pattern of crossing out happens the exact same way to every element on your list, every to-do that you finish. So the way we would define this, and this is just a reminder that that's what the Fibonacci sequence output is that we're looking for. So this function, this iteration version of the Fibonacci sequence is a little bit different. You can see that we start with 2 assigned variables, a and b, 0 and 1, and then we say for I in the range of 0 through n. So this is going to make a list, because we need a list to iterate over, that's as long as the number that we input. So in this case, it's a list that's 1 long. In this case, it's a list that's 6 long. And then what we do is we take that list, and then the logic that we use on every single item is that we make the item A the equivalent of what was B, and now we change B to what is A plus B. And that does the same thing as A plus B, and then it becomes A. A plus B becomes A. And we can do the exact same thing to get the Fibonacci sequence just as we expected, the 1, 1, 2, 3, 5, 8, and the 1, 1, 2, 3, 5, 8 up here. Maybe that gives you a little bit more of a sense of what it's like to work with iteration versus recursion. Let's talk about generators. This is a very powerful object inside of Python for its ability to work asynchronously, for its ability to pause its state. Let me just show you a traditional example of a loop that has the logic for squaring, because we're going to use this as a comparison for the generator one next. Just to remember how this works, we have a function, it's called loop squares. We're going to pass in these numbers, and then each number is going to get squared by itself, and then it's going to be appended to a list. So we have to start with a blank list. we have to run through each of the items like in the way we just talked about in an iterative way, iteration. And then on each iteration, we are going to append that result and then return the final list when we're done. So we run these two cells and we get exactly what we think. I did a type check here on the return numbers. It's a list. And then there is the list itself. So now let's look at how we would do that exact same thing with a generator in less lines of code and arguably in a more powerful way, depending on your use case. So this generator version does the same thing by starting a function. And it has the same inputs, and we're going to input the same numbers. We have for I in nums, which is the same as up here for each number that we have in the list. And it does take a list. We can't just put in the number 5 and it makes its own, although we could build it that way. But the point is it needs a list at this point before the yield statement. And then the yield statement, which you haven't seen before, a brand new keyword, is the equivalent of the logic, in this case append, but any other kind of logic too, and the return all wrapped into one. But it's a special type of return because it's not just returning any object, it is returning a generator object. The yield keyword is crucial for returning a generator object. What we're saying is don't just return any variable like a normal return can. We need you to send back an actual generator type of a variable. And because of that, we have the ability to keep some of the logic inside of it and execute it one by one. So what I mean by that is that if we run this function and then we look at the output, we actually have a generator object. Now remember before, we actually got back our list, and by printing the list, we printed the list. When we try to print the generator, we just print something that says, I am a generator. We don't actually print out all of these numbers. They're sort of unprocessed. They're more raw, you could say. And the reason why they're more raw is because we need another function after that to push through each step. So the logic for 2 times 2, which was done and then appended to this, has not been done yet. It's actually the logic. 2 times 2 is inside of the yield statement. It's inside of our object right here. So when we say next and then we look at the generator object that we got out, then we find our first result. So the number 4 comes out, and finally, only at this point, have we processed 2 times 2. So sitting in here, in the next step in the generator, is 3 times 3. It hasn't been done yet. But by calling the next function, we get it, 9. And so on, down to 16. So that's the difference, is it's bringing in the entire logic and waiting to execute it until the time is right. And there's certain reasons why working asynchronously is powerful, like something with a server where you're waiting for a response from someone, or there's some kind of thing that needs to happen before the logic is processed. So you can see how powerful they are. Another thing about them is supposedly they're a lot faster. Okay, now I'm going to be real upfront that these tests are not demonstrating what I read. I think I'm on the right track when guiding you this way, but I want you to be aware that I'm not solid on exactly why these times are coming out the way they are. When we use our timer function in Jupyter, what we'll see is the amount of time it takes to create this function, and then down here, how much time it takes to call it. And they're doing the same thing. They're both processing the same list, the numbers 2 through 6, and they're doing the same logic, the multiplication here. So arguably, one of the main reasons you would use a generator is because it saves time. It's not going to be as computationally heavy. It doesn't need to run through the entire list. You can run through it piece by piece on an as-needed basis. But beyond that, I actually thought that doing the generator by itself would be faster, like it's just a more efficient way all around to handle it. But with a use case this small, it comes out to be about the same amount of CPU cycles, so you might not see it, but I did want to show you how we could run something like this. So you can see up here on the wall time, it took 3.1. This is µs, which I'm going to assume is milliseconds, but I'm not 100% sure on that. But 3.1 for up here, and then it took 3.1 for down here. So creating the function, putting the yield logic together, or in this case, running the loop and appending all the logic to the answer, they took the same amount of time. But now when it actually comes to calling the function, down here and processing the list, you'll see that it took 5.1, and down here it only took 4.05. So even though we have all of these calls, it's kind of amazing. Like next generate object, which we think take more time. It's like starting and stopping all of this over and over again. You know, they do come out being more efficient as a whole. So my point is, if you're going to be working with a gigantic data set and down the road when you're, you know, a real high-paid programmer and you're doing crazy stuff with big data sets, you should revisit the concept of whether you should use a generator and see if there might be ways to get more computational gains out of it. As a beginner, it's not a thing to worry about, but it is a thing to know that there is time differences between the way we write code. Just one more example. It's just a different version of kind of what we started with, but I want to make sure that you see the difference in the yield statements. And I found out that surprisingly, my name backwards is super cool, and I was really proud of that and wanted to share it with you. We have a couple different functions here, one that's going to use a generator and one that's going to use a regular loop. So in this one, we're going to be importing a string of characters. In fact, my name, D-Y-L-A-N. It's going to be an argument that passes through here. We're going to get a number from this, the amount of letters minus 1. So we have 5 characters here. So this is going to return the number 5, but then we're going to decrement it by 1. So we end up with 4 in here. Here we're going to create a brand new list, an empty list with no items inside of it. And then we're going to make a loop. And we're going to say while the count, and this count up here is 4, is greater than -1, then I want you to append something to this list. And that thing that you'll be appending is the text count. So it will be this, and then in the slicing bracket, it will be this count. So it'll start with 5, and then 4. So what it'll be doing is appending that letter, then that letter, then that letter, each to this list. So this list is going to grow from being empty to being this, but it's going to work backwards and reverse my name. And then just to make sure that our while loop does eventually end, we take this count variable here and we decrement it by 1 using our shorthand notation, our shorthand assignment notation right there. Because this is a word, this is a string, we want to create a blank string called new, and we want to join this new list onto here. But we totally could just return the list too, but it just makes more sense, I think, in this case to make it a string. Dylan backwards is nailed. Like my name is nailed. Like nailed it, Dylan. Pretty cool, I think. But let's look at it in generator version. So here we have the same thing reversed. We're going to pass in an argument. We have the exact same argument, except we're making it into a generator and then running through each part of the generator using an outside for loop. Our inside for loop here, meaning inside of our function. So this is quite a bit different looking, but I wanted to compare the two so you could see that they actually could be interchangeable. We could use a for loop up here instead of a while loop. It would just look different. So I wanted you to maybe play with these two and kind of get your head around why they're different, but why they kind of work the same. And here we're taking that same string that comes in, my name, D-Y-L-A-N, and we're breaking it down into how many letters it is using the len function. So we end up with 5. And then we are minusing 1 in the same way we did up here. So we end up with 4. But then you'll notice these other two -1s, which are pretty unusual. So these allow it to loop around and then also to skip in increments of 1. So if you remember back to when we worked with our range function in loops, the range had a start, a stop, and it had a step function. So we can use all of those in this to create the kind of range that we need. So a little bit different than the count approach, but it works. And then when we're in here, we do a very simple piece of logic. Instead of needing append, which is only a method of the list out that we had before, we can just yield the logic itself, which is slice this right up and then put this into a yield statement piece by piece so we can get it out later. So when we run this, you'll see that we get the exact same thing. And in this case, we're getting it back out as a generator, so we don't need it as a list or a string. But you can see it totally worked. So we ran the function, we saved the return into a generator because we know it's a generator object, and generator objects can be looped over. So we just said for I in gen, print I, and then all of a sudden you get nailed. Thanks, nailed it. All right, you lovely generator people who know about recursion and iteration. Thanks for listening and enjoy the next lesson. Subscribe to our Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations. Welcome. In today's lesson, we'll be discussing the why of programming by reviewing mnemonics and having a discussion that relates to the following topics. Our first topic is going to be debugging. We're going to talk about what a bug is, the difference between bugs and features in the surprisingly gray area, and then we're going to talk about what the action of debugging actually looks like. Then we're going to move over to something called the stack trace. We're going to talk about what that is, how to read the stack trace, and what it means. We'll talk about exceptions. What are exceptions? We'll talk about the difference between a syntax error and an exception. And then to follow up on that, we'll talk about exception handling. We'll talk about what that means, why it's different from regular exceptions. And we'll talk about the keywords raise and finally. We'll talk about what the keyword raise actually does and what the keyword finally actually does. So remember that there's only 12 giant pandas in captivity in the United States. It's really not that many. So our first mnemonic today is going to be a wonderful ladybug, and it's going to represent the topic in general of debugging. And the reason I chose the ladybug for our mnemonic is because it has the word bug in its name, and it is a bug. It's double bugged, just like some of your code might be. So what is a bug? Well, a software bug is an error, flaw, failure, or fault in a computer program, or its system that causes it to produce an incorrect or unexpected result, or maybe even just to behave in unintended ways. And because unintended ways can be hard to define, it's the same reason why bugs and features come in many shades of gray. If you don't clearly define the functionality that you want to achieve, sometimes a bug becomes a feature or a feature becomes a bug. So what is the action of debugging? Well, debugging is the process of smoothing out these bugs or replacing the parts that are broken. Once you have a clear definition of the functionality you want, when that functionality always occurs, you have a bug-free code. But it'll almost never happen because there's so many use cases that you can't predict. So debugging is a spectrum, and it can be easy. It can be as simple as a print command that prints a variable at a certain point in the program and you notice that it's wrong and make a quick fix, or it can be as complicated as introducing new complex debugging code which just tests for subtle changes between your expected outputs and your true outputs. And there can be so many layers to this, both nested inside of functions, or in simple decision tree style complexity where you have conditionals that are layered on top of each other. So there's a big spectrum to debugging. So our next mnemonic is going to be a giant Jenga, and it's going to represent the topic of a stack trace. And the reason I chose this giant Jenga game is because the process of playing that game, Jenga, is sort of similar to a stack trace in the sense that we're looking up and down this pile, right? We're analyzing which pieces can be separated, which pieces can be moved, and we're guessing how that's going to affect the balance of the overall structure. And in the same way, we're looking up and down this code, trying to imagine how it's going to affect the overall output. So what is a stack trace? Well, a stack trace is a report. It's a report at certain points in time during the execution of a program. So it's going to take each line like a step. And we're going to be able to see a list of the method calls that the application was in the middle of when the error occurred, aka an exception was thrown. So let's talk about how to read the stack trace, because not every bug will have a stack trace, but many do. And if they do, this means that the bug's not on the surface level of your code, but instead it's wrapped up deeper down. And by deeper down, I mean that the order of the code that it's compiled in has different layers to it. And our bug might not be on the top surface layer. So it could be deeper in scope, like inside of a function, or it could be deeper in the source modules being imported. So instead of starting at the top of our code, we just start with our topmost method call. And then often this will get our attention close enough to the problem that we can work through the rest. So our next mnemonic is going to be China's red flag. And the reason why this represents the topic of exceptions is because it's literally a big red flag that you can remember. And exceptions should be thought of as red flags that need to be addressed. So what is an exception? Well, imagine if somebody passed in a string argument when your function only works with integers. Exception handling is how you deal with this. So what's the difference between a syntax error and an exception? Well, syntax errors, which are also known as parsing errors, these are syntax problems, and I think of them similar to just misspellings or typos. You probably just typed something in wrong, and if you look closer, you'll see that you're missing a semicolon or something like that. But even if a statement or expression is syntactically correct, it may still cause an error, and in those cases you have an exception. And the reason I chose this for the mnemonic is because in the same way that a practical joke works, exception handling is all about bringing attention to the unexpected. So what is exception handling? Well, exception handling is about making sure that we have variables that don't break our code in some way. So this is going to be similar to how we had our conditional section before. We're going to want to do exceptions to make sure that our variables are what we expect they are at the right times. Exception handling is a process of responding to an unwanted action during either the compile time or the runtime, which we'll talk about in a second. So we're going to want to know a couple keywords for this, specifically the keywords try and except. Going back to the conditionals, these are very similar. Python gives us these conditional type keywords to help us find where our code goes wrong in the sense of a variable not being what we expect it to be. So let's zoom in on this try keyword. So kind of like our conditional that had an if statement where we could say is something equal to some variable, our try statement is going to check to see if the exception is the type that it expects. So remember, when we have an exception, there's already a type that it can have. When we downloaded Python, many of these exceptions already exist. We can add a few more, but there's already dozens and dozens that come with Python. So that's what we're going to be checking for. And we have a few options. We can try with no exception. We can try with a match type, so the exception we get matches the one that we're telling it to look for. Or we can try with a type mismatch, meaning if it's anything except the one that we want. So let's talk about trying using the keyword try with no exception. So first, the statement between the try and the except keywords are executed. You'll probably be able to see this better in the next video when we're actually looking at code examples, but you can imagine it a lot like our if statement from before. And then if no exception occurs, the except clause is skipped entirely, and the execution of the try statement, it's finished. Then we also have try with a type match. So in this case, if an exception occurs during the execution, the rest of the clause is skipped. And then if its type matches the exception named after the except keyword, the except clause is executed, and then the execution continues after the try statement. And then finally, there's try with a type mismatch. And sort of the opposite to the others, if an exception occurs which does not match the exception type named in the except clause, then it's passed on. I feel like you'll probably understand that better in the next lesson. So even though I said the things right, I think it's like all over the place until you sort of see the spacing and stuff. So roll with it in the next video. So now let's talk about a couple more keywords that go along with that. And we're going to use the mnemonic of a cosplay woman raising her sword. And it's going to represent raise and finally. Two more keywords that we're going to use for debugging. And the reason I chose her as the mnemonic is because when you see someone looking at you, and then they raise that sword, you know something's wrong. And these will tell you something's wrong too. Just, these are exceptions. That one means you're going to get killed. Okay, so what does the keyword raise do? Let's focus in on that one first. So raise is a way to override the default exceptions in a way that we want. So what does the raise keyword do? So let's focus in on that. Now, the raise keyword is a way to override the default exceptions in any way that we want, so we can display information that we need to other developers and to users. So I mean, in a nutshell, raise just allows us to define our own type of exception errors. And really, you don't need this too often. Python has the main ones already built in, but every once in a while you have a special use case where it's good to know that you can do this. Now, how about the keyword finally? What does that do? Well, we can use the finally statement to ensure that a block of code is closed at the end of the file, even if there is an exception that causes the interpreter to break. So we have something that stops right in the middle of the code, but we still need the code to jump to the bottom and close something up or release something to make sure that it actually is pulled away in the correct way. I kind of imagine like on your computer when you like pull out a USB stick without clicking the thing, and it's like, like that's the way you can think about this. So times when you might want to do something like this is when you need to close out an open file at the very end of your program or something like that. And for our final mnemonic, I want to group together some of these exceptions into runtime and compile time exceptions. So our mnemonic, a marathon runner, and I chose a marathon runner for the runtime and compile time because a marathon runner is keeping track of their run times, like on their watch, and then I also think of the compile time as maybe the big number thing that you'll see at the end of like runners, their big finish line number, you know. And also, I kind of think compile time sounds similar to a mile time, so you might want to think of it that way too, but that's up to you. So now let's talk about grouping these errors into two different groups, one for runtime and one for compile time. Now, starting with compile time, this is when we're first executing the code on our end, not when the user is actually using it. Compile time errors happen when we feed in a whole bunch of text to the compiler. It's reading the code that we just wrote, and it's converting it behind the scenes into machine code, ones and zeros. So these compile time errors are usually syntax errors, meaning we type something wrong. They're type checking errors, like where we use a variable that's, say, type string, but we're using it like it's a type integer and it doesn't know what to do. And then in rare occasions, like never happened to me, but when I read the documentation, it said it happened, there's compiler crashes, where you just have to like shut your IDE down, or the Jupyter Notebook breaks in our situation. Okay, and then there's also the runtime errors, and these are the errors that will be used when somebody else brings up our program, and there could be, say, a division by zero, meaning somebody put a zero into our code from the user end and it did something weird, broke, gave us an error. Great staying with me on this lesson. So let's end with a quick summary of the mnemonics that we just learned and the concepts that they represent. Now, our first mnemonic was a ladybug, and it represented the topic of debugging in general. We learned that bugs are pieces of code that produce unexpected results. We learned that bugs and features come in many shades of gray. And we learned that debugging is the process of smoothing out these bugs once you have a clear definition of the functionality that you want. Next, we learned the mnemonic of a giant Jenga set, and it represented the topic of a stack trace. And a stack trace is a report, and this report can point to different points in time as the computer compiles our code, and some different techniques to read this stack trace and understand it. And our next mnemonic was a giant Jenga, and it represented the topic of a stack trace. And we learned that a stack trace is a report, and it's a report that talks to us about our code in different points in time as it moves its way down the code from top to bottom. And then we talked about some of the techniques to look at the stack trace and get some intuition about what might have gone wrong. Then we learned the mnemonic of China's big red flag, which represented the topic of an exception, and we learned that exceptions occur even when we have written our statements correctly, and it often has to do with what's inside of our variables. After that, we learned the mnemonic of one of those hand buzzers that like a clown would have, or the Joker, and it represented the topic of exception handling. It's how to handle those red flags. And we learned that exception handling is the process of responding to the unwanted actions, either during compile time or during runtime. And then we learned the mnemonic of a warrior princess as she raised her sword, and it represented the keyword raise and the keyword finally. And zooming in on them, we learned that raise is a way to override the default exceptions in any way that we want, so we can display information that we need to the users and other programmers. And then we learned about the finally keyword, which lets us run a special block of code at the end of our file, which helps us either disconnect from a server or close out a file or something else that might cause a problem if we don't make it all the way through our code. And our final mnemonic was a marathon runner who is keeping track of their run time and also looking at their final time on the finish line. And this represented our runtime and compile time errors. So we learned some of the things that would happen at the different times and which kind of errors would be grouped into which ones. And then our final mnemonic was a marathon runner, and he was keeping track of his run time and then also his finish line time, and this represented our runtime and compile time errors. And then we talked about how different errors can fall into these two different groups. So I think we've had enough theory for now. Why don't we pull up our old trusty Jupyter Notebook and start looking at some of these examples in code. Subscribe to our Mnemonic Academy YouTube channel for daily uploads that will help you learn amazing concepts through effortless associations.